So I think we can start if we are all here. So welcome to the parallel session of the Marcel-Grossman meeting. This is dedicated to the Gamma Bar 170817. And we will have 7 talks, and these talks will last for 20 minutes, plus we will have 5 minutes for each talk of questions. And the first talk is Francesco Panarale with the robustness of the association of gravitational wave event 170817 with the gamma ray burst 170817. So Francesco, if you would like to start, please go on.
Yes, good afternoon. I'll try sharing again. You should be seeing this now. And it will be full screen in a second if I can move stuff out of the way. There. Is it full screen?
Yes, fine.
Yes, okay, yes. So Julia, thanks for the invitation. It's a pleasure to start this session. I won't repeat all the 17 and 08s in the title, so I'll dive right into this. And it's not letting me switch around. There we go. So the first thing I'd like to recap on, even though I'm sure we'll hear about this several times, is that, you know, for years ago, there was this nice and clear track observed by the LIGO and Virgo collaboration in the 3 interferometers you see on the left. And this was found in low latency first in a single detector, and then confirmed offline with, you know, a full steam analysis with several searches, actually, not just one, even more than one. So whatever we threw at this event, we kept finding it as a very, very confident and loud signal. And once we ran the parameter estimation codes on this, it was clear that the signal is consistent with the in spiral of a binary neutron star source, so 2 neutron stars. And the other nice feature of this signal is that for LIGO Virgo standards, it was localized very well as a triple detection. So the 90% credible region of the localization area was of about 28 square degrees. And you can see a little projection of this in the sky. And this is the green region that's localizing the source of this event with 3 detectors, whereas the 2 blue distinct arches are the localization obtained with only 2 detectors, so with the 2 Livingston instruments. So in this case, having a triple interferometer network really made a big difference in terms of localizing, and then further down the line enabling multi-messenger astronomy with gravitational waves. So independently of what was going on in the gravitational wave world, there was a detection of a gamma ray burst by the GBM gamma ray burst monitor instrument on board of the Fermi satellite. And this event, 1708-17A, triggered 3 of the detectors on board of this observatory with a signal that exceeds more than 5 sigma. So even for GBM, you know, independent of our gravitational wave signal, there was an event, a GRB, which was a very confident one. And you can see the event rate as a function of time in these histograms, in the 3 histograms on the top of this plot. And the 2 top ones are the ones of the coming from the GBM data, and they're divided into energy bands. And then in the more energetic one, so the second one from the top, you'll see something that looks like a standard triggering pulse, a rapid one, half a second more or less. And then there's a falling, softer and weaker emission that is evident in the top band in this event rate time series. And the GBM analysis found that the T90 of this event was of 2 seconds plus or minus 0.5, fluence of roughly 10⁻⁷ erg per square centimeters. And based on the duration of this event and alone or with the spectral hardness, GBM classified this as a GRB that is 3 times more likely to be short than long. Now, their localization was not as good as the gravitational wave one. The area is larger, roughly 1100 square degrees. But then this information, we'll see, becomes very precious. And the other important bit of information is the delay between the GRB trigger time and the gravitational wave trigger time, which is reported here on the bottom. It's roughly 1.7 seconds. And again, it's not, oops, how do we do this? There, okay. Again, at the same time, other gamma ray satellites and observatories are flying around. And there was an observatory SPIAX on board of Integral that followed up the GBM trigger and found evidence for a GRB in their time series as well. And this is the third row in the plot on the left with the event rate as a function of time. And they clearly see an excess at the same time of the GBM trigger. The SNR isn't exceptionally high, but it's there. The fluence, once they analyze their light curve, is consistent with the GBM one. And interestingly, only the timing association between the integral observation and the Fermi observation places the integral, the SPIAX observation, as a 4.2 sigma outlier. Basically, this is asking the question of whether the two events are disjoint, and based on timing only, there's a Gaussian equivalent significance of 4.2. So an outlier, it would really be an outlier to have caused some distinct distributions to bring these two observations together. And SPIAX made the statements, the collaboration rather, that alone it would have not reported the event, but it would have found it following up the time around the gravitational wave detection. And if the temporal association of the gravitational wave detection and the SPIAX observation of this GRB is calculated, the independent association has a Gaussian equivalent significance of 3.2. So even SPIAX is seeing this as a GRB, as a short GRB, and it basically finds it whether it tracks the gravitational wave event or the Fermi reported GRB. So right now up to here we have independent observations of possibly independent events. They are localized pretty close to each other in time, again 1.7 seconds apart from each other. The sky maps have a region where they all overlap, as you can see in this plot. And the question that arises naturally is whether these events come from the same physical event, so from the same source and physical process. And the rest of the talk is dedicated to answering this question. So first, there's the frequentist approach to trying to answer this question. And then there's a more thorough Bayesian approach to the same question. So what the frequentist approach can do is basically test the null hypothesis and evaluate how likely or unlikely it is to observe the GBM event and the GW event as independent Poisson processes. So what the frequentist question that can be asked is whether by chance these two events, these two observations are this close in time and this close in spatial localization. And since the timing and the spatial agreement are disjoint, we can first tackle the timing question, then the spatial one, and multiply our p-values together, basically. So the probability of this temporal association by chance is shown in the orange equation here. there's a term that's the time delay, a term in front of it that accounts for the fact that you could have if the coincidence is by chance, you could have the gravitational wave before or after the GRB. So there's a factor 2 there. And then there is the observation time of Fermi GBM, basically. And we're factoring in here all the time that GBM had been functioning until this event, so 3,324 days, the number of short GRBs it had seen, which is 351 until then, and then the lifetime of the detector. So part of the time the detector is off to preserve it from the South Atlantic anomaly, during the South Atlantic anomaly transit. And there's a factor of 1 you don't see here, which back then stood for the fact that the LIGO-Virgo collaboration had seen 1 event only in the whole time it had been running. So multiplying all these terms together, you get this p-value of 5 times 10 to the minus 6, which basically means that this is a 4.4 sigma Gaussian equivalent significance. For the sky position, you have to do something a bit more convoluted, perhaps slightly less intuitive. So you define a statistic, which is here in the equation on the left. And basically, you're taking the posterior distribution, so the 2 sky maps seen from the gravitational wave end and the GRB end. These are pixel maps, and pixel by pixel, you compare the maps. And you're basically multiplying in each pixel the posterior probabilities and summing over the pixels. And this will give you statistics of how well these maps agree. And then you have to establish the significance of this. So the frequentist approach needs a background to do this. And the background was generated by taking 164 localizations performed by the GBM, let's say, procedure pipeline methodology that is similar, well, it really is identical to the one that had led to this specific localization. Given these 164 maps, they were, each of them was randomly shifted around in the sky and rotated 10 times. So you have roughly, 1,640 sky maps as a background. And then you repeat the calculation of the statistics on the left, freezing the GW map and running over all these randomly generated background GRB localization maps. And then you compare this background distribution to the value obtained with the original 1708, 17A localization. And this gives you a p-value of 1%. So it's a lower Gaussian equivalent significance compared to the timing agreement. But once you multiply the 2 together, so these 2 p-values you obtained are independent, and you can multiply them to obtain the overall p-value. What you get is a 5 times 10 to the minus 8 overall p-value. So 5.3 sigma Gaussian equivalent significance. And this is a measure of the null hypothesis. So the question you're asking here is, if I assume the coincidence in space and time happened by chance, what is the probability of this happening? It doesn't really tell you that these 2 signals come from the same event. It's telling you how probable or likely or unlikely it is for them to have happened by chance. So can we go beyond, just testing the null hypothesis, so quantifying whether this only happened by chance? The answer is yes, you can do this with a Bayesian approach. And the quantity to calculate in this case is the odds ratio between the hypothesis that assumes that the 2 signals, GRB and GW signals, come from a common source. So there's a superscript C all over the place for this. And the hypothesis that there are 2 distinct signals. So SS, signal in the gravitational wave world, and in the GRB world. And the odds ratio is the product of the priors you have, on the ratio of priors, really, that you have on the two hypotheses, and a Bayes factor. And the Bayes factor itself is then the ratio of the likelihoods of obtaining the gravitational wave data set and the GRB data set under the common hypothesis or the distinct signal hypothesis. And there's this, this first line is, if you speak Bayesian, I guess, is fairly straightforward. And then there's this paper quoted here on the bottom right that goes through the calculations. So what takes you to the second line here in this slide. And this basically shows you that you can calculate the odds ratio between the two hypotheses as the product of the prior odds, this product of disjoint likelihoods, and then an integral which measures the overlap of the posteriors of the gravitational wave data set and the GRB data set over the space of parameters of the hypothetical common source. So this last term, I calligraphic, is really an integral over the parameter space of the posteriors on all the parameters, ideally, in light of the gravitational wave data set, the common hypothesis, and the posterior for the same parameters in light of the GRB data set and the common hypothesis. And the denominator is just a scale against which to measure this overlap and normalize it. So they lay out all the foundations in this paper to perform this calculation. And then, this is all nice and tidy in mathematical terms. Then you actually want to pull out numbers, and you have to start making some assumptions and simplifications to begin with, so that you can place a lower bound on this odds ratio we're interested in calculating. So the first thing you can do is to restrict the parameter space to basically, as before, as with the frequency approach, to timing, to temporal parameters, time of arrival, and the direction in space, which matches the sky maps we were talking about earlier. So this restricts, the calculation they perform restricts everything to the same parameter space we used in the frequentist approach, sorry. Then you have to make assumptions about the instruments you're dealing with. And the simplifying assumption here is that all the instruments that come in play, so GBM and the LIGO Virgo observatories, are all sky observatories, and they don't have preferential directions. And so in general, as the Earth rotates, this is basically true, and that their sensitivities are stationary. And this allows you to reduce, to simplify all the ratios there are here between likelihoods on the second row. So what survives is the prior odds and this posterior overlap integral. I will switch again, and you'll see the middle factor disappear. So here we have that now with these assumptions. The odds ratio is the product of the prior odds and the overlap posterior integral. So now the difficulty, let's say, is calculating this last term. And you can do this assuming that the coalescence time is determined exactly from the GW data. This gives you a delta function. You're basically neglecting the timing error in the gravitational wave data. And indeed, it is a small error. And at this point, you can say that this integral is the product of integrals, the overlap of the posteriors in sky localization and the overlap of posteriors in timing. And for the timing, this overlap vanishes unless the GRB happens in a specific window where we search. So 6 seconds asymmetrically distributed around the gravitational wave trigger. So if the GRB is too far from the time of the GRB is too far, so outside this window, compared to the gravitational wave trigger, the overlap is 0. Otherwise, it's the ratio of the observing time of GBM, and the search time window of 6 seconds. So this I'm putting the numbers here directly, but you could repeat the calculation for different time windows. This is the, let's say, well-posed time window we generally search around or within. And for the sky coincidence integral, overlap integral, you repeat what we did earlier. You take the posterior maps and run them in the definition of the integral. If the posterior maps are not available, you can even simply take a uniform posterior distribution over the size of the localization areas, and roughly you get the same result. And at this point, all we need to define is the prior odds. And if you assume that the common hypothesis, you are basically dealing with a Poisson distribution where you've had one event, and this is regulated by a rate of common detections times the observing time. Whereas if you assume that the denominator, if you assume that the signals are disjoint and are independent, you have the same thing, the same kind of Poisson distribution, but you have only the gravitational wave detection rate for the GW signal and only the rate of GRBs for the GBM signal. This is a low event statistics. Approximately, this becomes the ratio of the common detection rate divided by the product of the disjoint rates times the common observing time. And since again we roughly have seen one BNS, order of one BNS, and we've had one common detection, you can simplify two terms, and this becomes 1 over the rate of GBM detections and times the observing time. We know the rate of GBM detections, you plug it in there, and all in all, summing everything I've said in this slide, you get this lower bound of 10 to the power of 6 on the odds ratio. So this analysis says that it's 10 to the 6 times more likely. Well, the common origin hypothesis is 10 to the 6 times more likely than the disjoint signals hypothesis. So in summary, and again, the details are in the papers and then in the presentation, we have a very confident GW detection on one side, and it's compatible with the in-spiral of two neutron stars. These are the 90% credible intervals on the two masses. And we have a short gamma ray burst witnessed confidently by two distinct instruments. And by eye, the timing is good of these different observations. The sky localization is promising, and naturally one is pushed to ask the question whether they are robustly associated. And we took a first stab at this back in 2017 with the frequentist approach. And again, this looks at p-values, so it's testing the null hypothesis. And the final statement is that the agreement between the GW and GRB data can happen by chance with a 5.3 Gaussian equivalent significance. A step beyond this is to really compare hypothesis. And in this case, modulo some approximations, we can say that the common source model is favored over the disjoint unrelated signals model with the lower bound of roughly 10 to the 6. So in conclusion, the two sets of observations are robustly associated. And this was the last slide I had. I will stop sharing to read questions and share again if I need more slides to answer questions.
Thank you very much, Francisco, for this very nice talk and this very important clarification. Are there any questions?
Yes, I do.
Not by Sebastian.
I don't know how to raise the hand. So I have a question about this overlap that you show. Of course, computing this in general, one should consider all the correlation between the two events, so the models of all the events. So do you have an idea, how much they would impact? Sorry. Do you have an idea how much they would impact? So considering more than position and time, if you start to consider other parameters of the source and so on, and all the correlation between those, what would be the change?
So everything should increase because you'd narrow down you're basically adding constraints in the parameter space. I have no intuition for how quickly this 10 to the 6 goes up as you add parameters. But basically, yes, lowering the amount of information you use in this overlap integral, or restricting the dimensions of the parameter space is allowing you to place lower bounds. You're using less information, so you're not weighing in all these correlations and constraints there are. So it can only go up, but I wouldn't know how quickly.
Yeah, I'm of course asking not for this event, for future events in which this establish the same would be much more difficult, right? So maybe if such analysis would give you an evidence of, I don't know, of order 1 or 10, maybe adding few parameters which are model dependent, more model dependent in the case. So you also introduce more uncertain analysis, but
yes,
maybe it could. Sorry, I don't know what's going on here. It could higher it of a factor 10 or hundreds maybe, and then in a model dependent way you would claim a more confident association.
Yes, you could increase by orders of magnitude the result, but the price to pay is a model dependency, of course. That's right.
Okay, thanks.
Okay, so if there are no other questions, we can move to.
I have a question, but
yes,
just very quickly.
Go on.
Sorry, Francesco. At some point you say that at the beginning that there was a factor that was not showing the slide, factor 1, because it's just one the event that was observed by gravitational wave and GBM. Is this? I mean, of course, GBM also was trying to observe also other gravitational wave events, so it was not very clear to me.
So I think you're referring to what I said here. Let's see. Oops, no, I have to share again. This, right?
Yeah.
I think it was here. Yes. So basically here you have the third term is GBM world. So it's the rate of GBM observations. And you would have to multiply by the rate of GW observations times the LIGO Virgo observing time.
Mm-hmm.
So this, until 1708-17, this was 1 BNS over the observing time till
until okay, that's now it's clear.
It's
okay.
the same thing.
It's not until now, until that time. Okay,
yes,
so
until then. So yes, this will change things by a small factor, but yeah, it won't kill the 10 to the minus 6 completely. And then of course you would have to change the GBM slightly, the GBM numbers if you want to repeat the calculation up until today.
Thank you, it's clear.
Okay, so we can move to the next speaker. That is Sebastiano Bernuzzi. That he will talk about numerical relativity modeling of the ejecta and kilonove from binary neutron star mergers. So please, Sebastiano.
Yeah, also let me thank you for organizing the session and inviting all of us. Let me try to share. Do you see the presentation now?
Yes.
Okay, so this seems to work. Yeah, so as the title says, I want to change a bit the focus and talk about what happened later, and not only what happened later observationally, but more on a say theoretical point of view, and summarize what I think we know and what I think we don't know about the connection between this kilonova signal that was detected after the GRB and the actual source. So this is all about simulation and numerical relativity exploration of this binary neutron star collisions or mergers. And here is a summary of the picture that we have all in mind. And what I want to focus is, of course, not the pre-mergers, not the spiral motion, but what happens after merger. And I think the main message that I want to pass you here at slide already 1 is that from a theoretical or simulation point of view, we know things with a different degree of confidence regarding different phases. So in particular, we are rather confident that we are simulating with enough physics and that we have enough understanding, probably not complete, probably not with all the quantitative detail, but still sufficient for an early, for what concerns the simulation of an early phase after merger. Say tentatively the first 10-20 milliseconds after merger. This is a phase in which the dynamics is still gravitationally dominated. It's the phase in which the remnant can collapse to black hole. It's the phase in which dynamical ejecta, which I will talk about, are emitted. It's also the phase in which there is the bulk of the emission in the kilohertz regime. And so everything that somehow numerical relativity can say, with some caveat, but many things that numerical relativity can say and predict from this phase, I think are rather robust. And so they can be used for astrophysical interpretation rather confidently. But there's a later phase where gravitational waves have been fully dispersed and emitted, in which we know much less. This is what we call this viscous phase. So it's the phase up to seconds after merger. And here, this is a phase in which there are many complicated processes that dominate the dynamics. So from magnetic fields, neutrino are perhaps the most important.
Posso intervenire?
Yeah. Feel free to interrupt.
Vuole fare una domanda.
Ramo, if you want to ask a question, if you want to do it now, go on. Otherwise, you can wait the end of the talk. And,
Thank you.
If you want to make, okay. So.
This is the phase in which determine, for example, the remnant outcome, winds, which are very important to study kilonova. And also it's the phase that connects to the electromagnetic epoch. And this is the phase that we know significantly less, and for which possibly we don't even have the full technology developed for that. So these are the two. This is the message that I would like to send. So for what concerns kilonova, we know that this is most likely produced by nucleosynthesis that happens in mass ejecta. The idea is rather old, and it's the idea that if some mass becomes unbound during merger, this is neutron-rich matter that expands and cools down and creates condition for our process nucleosynthesis. and during this our process nucleosynthesis, beside creating heavy elements, there's also characteristic thermal radiation that has been predicted since a long time. And there are many simulations about this process that has been refined consistently during the time. And what perhaps strikes more from the literature is that The conditions in which this our process nucleosynthesis happens are very general, and the prediction, say, for the element abundances are very robust, rather independent on the details of of the merger, what objects are merging, and so on and so forth. Although we will see that there are in the fine details there are these imprints. And now to say something that is to jump basically to our time. What is interesting of this signal is that it can allow improve analysis, or if you want, multi-messenger analysis of gravitational wave and kilonova signals. And this is one example. Perhaps this was one of the first pointed out. Essentially, what happened for the gravitational wave in August is that we could place, through the match filtering analysis, we could place a upper bound on the reduced tidal parameter, which is a parameter that essentially identifies the source as made of neutron stars, and is strongly related to the equation of state of the matter there. But this was only an upper bound. However, using the luminosity and also the color of the kilonova observed, and using numerical relativity modeling, one can argue that the characteristic of the signal are such that there must be a lower limit in the same parameter, at least for comparable masses. So in putting everything together, what you get is that a reasonably robust and tight interval in which this parameter has to fall, which constrain in the end the matter properties of this neutron star. So as the slide indicates, the key element here that has been used to put these constraints is precisely numerical relativity modeling. And in particular, the observation that the disk of the disk created in the remnant has a somehow correlation with this lambda tilde parameter. And so certain characteristic of the spectrum of the kilonova can be associated with the presence of a disk, and so it can be and from this one can select a lower limit on this reduced tidal parameter. So this is an example application of numerical relativity directly within observation. So this has been refined, I would say, significantly in recent year by not many, but by few groups. And so this is an example of what are now bit more modern and I would say rigorous analysis than the previous slide. Here, what we have done is to perform a full Bayesian analysis of the kilonova by using a flexible model that allows to consider different ejecta component and also different geometry of the ejecta. As we will discuss later, this is rather important. And we have compared we have done model selection and compared the different model against the data. And what it turns out is that the data prefer kilonova light curves that are produced by models that have more than one component, actually 3 components in this case, and also that they have anisotropic geometries. So this is precisely what we observe in simulations. That's one of the reasons why we did. That's why we did this analysis. And as a byproduct of this analysis is that just using, I would say, the most robust numerical relativity information, so excluding this disks, evolutions, and late part of the evolution, one could put a relatively tight constraint on the neutron star radius which are in line somehow with several previous analyses, not all done in this way. Actually, most of those are completely different analyses. And so there is a clear picture emerging here for the constraint on the radius. So these are some example application. And now I wanted to show you, I don't know how long I have, but just interrupt me when or if you can tell me when it's 5 minutes.
Yeah, okay, I will.
I wanted to show you what is behind this analysis, and just starting from this dynamical ejecta. This is the material that is becomes unbound at the very early stage, so basically around merger. And it's typically, at least in general relativity simulation, is observed that is composed of at least two components. One, it is due to tidal, to some tidal tail from the stars, and another one that instead is generated after the star have collided, and actually at the first bounce of the two cores, as this middle plot illustrates. And so the two components have also very different composition. One, of course, is called the neutron-rich. The other one comes after an hydrodynamical shock, so carries a higher electron fraction. And they also have different geometries. And so depending on the binary property, say if they are equal masses, or which equation of state is, if the equation of state is particularly soft or stiff, one of the two components can dominate in the total dynamical ejecta. This is material that has typical masses of 10 to the minus 3 solar masses, so it's very, very little material, but this is sufficient for having signals like the Q-nova that we observe, at least in part. This material is ejected with average velocities that between 0.1 and 0.3 c, but this is just an average. There are high-speed tails that are pushed out, and these peak tails are interesting because they are mainly responsible for synchrotron radiation that could emerge, for example, in X-ray or radio band after many months or years after the collisions. And so these have been studied by various people. Is in some sense numerical is the simplest thing to do, but there are subtle issues. First of all, you need to study general relativity, otherwise you significantly underestimate this shock component. And also, as we will see, it's very important to include the neutrino heating, which is something that not all the numerical relativity groups, for example, are doing. Something that perhaps I'll skip this due to time reason. And so here is a comparison between the best model, or would say some model fit to the observation in boxes, blue and red, and actually targeted simulation that we have done in the previous year. And the box correspond to the simplest spherical two-component model, whereas the points corresponds to the mass and the velocity and the average electron fraction of different ejecta component, and also there are upper limits for this squint. And so, as you grasp immediately from this plot, even without understanding the detail, is that interpreting this fitting model with two components, spherical fitting model, as one of the components that we actually observe in simulations, for example, as dynamical ejector or winds, it is not really possible. So in other words, spherical two-component models are good fitting models, but they are incompatible with what numerical relativity predicts. One way to go beyond this, of course, is to consider more sophisticated model which take into account geometry, which take into account multiple components, and then the fit values, if you want, from the observation, they improve with and they get close to what we predict in numerical relativity.
You have 5 minutes. Sorry.
Okay, this is what I mentioned before, and it's one of the critical aspects that I think are still open in the simulation of the dynamical ejecta, and is the inclusion of neutrinos. So here you see histograms of max fraction distributed in the polar angle for the same simulation, which is performed in two ways. One only with neutrino cooling, and one also including heating. And you see clearly that not only the composition is very different, especially in the polar region here, but also the geometry, and we will see also the mass is really affected. So something that is very important for the future would be to have neutrino absorption effect included in the simulation. And at the moment, this is a challenging aspect in general relativity, and there are only a few groups that are, actually capable of simulating this. And here is something that I already mentioned. These are essentially all the data available from numerical relativity simulation and dynamical ejecta. And in different color, what is colored are different treatment of neutrino interaction in the simulation. And you see that, again, if you don't include any weak effect, you have these gray points scattered all the way around. But also if you include only cooling, you significantly underestimate the mass, and you have typically much higher velocities. So it's really important to have an accurate description of neutrino. And then moving to, later stage of the simulation, we move towards a regime in which basically there are no 3D simulations that are sufficiently, complete in terms of physics, in terms of time span, in terms of accuracy in general. And this is kind of the new territory that I was mentioning before, in which us, numerical relativists, still have a lot of work to do. But we know about this. So this is a tentative exploration of a long-term simulation in 3D, putting all the physics that we can put inside. And you see that, surprises starts to appear. In this case, what one can discover just by using, ab initio simulations, is that if you have a neutron star remnant, there is a wind that emerges after the dynamical ejecta from an interaction between the central remnant and the outer layer of the central remnant. So this 3D thing is the transport of angular momentum outside, which ultimately, of course, leads to the to the wind, to some wind that is inbound. And you cannot discover this if you don't start from the very beginning, because you need the exact condition determined by the merger to see this phenomenon. And this, for example, is something, including this wind, is something that is rather important, or can be important, to explain the early blue component of the observed kilonova. And the reason is that here in this wind, you get a material reprocessed that undergoes weaker process, and so this contribute to the early optical emission that is called as the blue peak. And again, this is if you include also the spiral wind, you have this nice nucleosynthesis predictions. They robustly produce the third and the second peak, as we all know. But you see that both equational state differences and mass ratio differences in color, they can give very different prediction of the first peak. This is kind of expected. Is mainly related to the kind of remnant that this combination of mass ratio and equational state produces. I will unfortunately, I have to skip this, but I will perhaps comment at the end. And now here are the open questions. So these are the kind of remnants that we currently predict. We know how to characterize certain remnants with neutron star components. We know how we know how to characterize black hole plus disk remnants, but their evolution from now on has not been studied in 3D and starting from realistic conditions essentially. And the wind from this disk is actually, as shown here in this plot, is actually the most massive, produces the largest contribution to the kilonova. And so we don't have for this the same handle as on the dynamical ejector. But this is important, for example, for the multi-messenger application that I have mentioned in one of the early slides. And associated to that, what also we don't know is how this remnant would keep on evolving. We certainly know they will keep on evolving, because what we find is that all these, for example, all these neutron star remnants produced after merger, they all have angular momentum and mass in excess, significant excess with respect to equilibrium configuration. So while these systems are almost axisymmetric, they are very far from the stability regime. And this is described by this rest mass angular momentum plot that I'm showing here. The gray region is the equilibrium region for cold equilibrium. And the point here in yellow is what we predict after a certain evolution. And so you see that there must be evolution because this object is not in a stable region. And it's also very massive. One would be tempted to say, okay, this is like an hypermassive neutron star and is going to collapse to black hole. But this is actually not true. If you calculate analytically some simple model for the ejector, for the wind emission, or if you even start to extrapolate the simulation, you see that there could be such a massive ejecta from the disk that would bring this highly massive remnant into the stable region. And vice versa is also true if for models that, for example, give masses below this cusp, which is the Kepler limit. So the summary is that the quantitative prediction of the fate of the merger after, I don't know, 5 or 10 milliseconds is very entangled to the to the full evolution and to the winds that can develop from the remnant. And you need a very comprehensive approach, which currently is not fully developed in numerical relativity, to tackle this multi-physics and 3D and long-term evolution problem in some sense. And so this is a summary slide, and I'm again going back to my two early points. There is an early phase in the post-merger in which dynamical ejecta and collapse is relatively well studied, or we have the technology to do that. But there is also an interesting and absolutely necessary late phase, the viscous phase, to understand in order to really connect the observation to the source. And yeah, let me finally mention that this is our simulation effort, only in part. Most of the data is public to all of you and should be in a in a friendly format, so that all of you can attempt an analysis based on numerical relativity data. And just to launch one of the next talks, some of this data supported this analysis or this X-ray analysis at very late time based on the kilonova afterglow. So I think I'll stop here. I'll take questions since there were already some questions.
Okay, thank you very much, Sebastiano. So please, Remo, if you would like to make some questions. if someone has some questions, go on, please.
Maybe I have some remark. I have heard speaking about a robust first phase of general relativity and a second robust phase of the kilonova. It's very interesting. However, I think all this input that you put on general relativity for this system on the first robust phase, the second robust phase in the kilonova, and the last phase that you are speaking, vastly overcome the energy observed in this system. But I don't want to add anything at this stage, just to let you know this. And of course, it's not difficult to make a robust analysis on general relativity. It's not difficult to do a robust analysis of kilonova, but it's to be demonstrated that this robust analysis have anything to do with the system we are observing. And one of the ways to evaluate the total energy. But this is just a remark. Okay?
Okay.
I have just to, I wanted to intervene just to tell this, and I let you to a successful meeting. I see Elena there, and this makes me happy that she can enter.
Yes, hi Remo, I'm here.
With some good remark. Okay, I have unfortunately to follow the other 29 session, but I think this of the energy, keep in mind, is the key. Okay? Okay, bye.
Bye.
Okay. So John Beatty, if you have a question, please go on.
Hi, Sebastiano. I was going to ask you about one of the slides towards the end where you were showing the evolution of the disk and post-merger remnant, and you said it could potentially even end up as an equilibrium neutron star. I wonder if you want to flash up the slide again, but
Sure.
the question was like, how long can this object survive? And is there any difference from this kind of generic 10 seconds I think you put in your first introductory slide? Yeah, so how long would it take to evolve into this state, or in general just to evolve?
Yeah, thanks for the question. So here is the open question. I don't think that the time of evolution is particularly relevant. Maybe for astrophysics, I don't know, but I would not consider a priority question. But as a time scale, you do enter here in some secular time scale. So, I mean, here the processes that, so for example, the yellow point is at the end of this gravitationally dominated post-merger phase, which typically lasts 10 to 20 milliseconds. If of course, you don't have a black hole before. Then the rest of this black line here going down is the next 1 or 200 milliseconds that we simulated afterwards. And so you see that for a while, this is more or less constant in rest mass, and after a while, this goes down, and this starts to be the emission of the disk. But then this can go on, well, until there is disk, for example. But this can go on for hundreds of milliseconds or seconds. So you enter here a regime in which it's not anymore the time scale of the gravitational wave, but is the time scale of the magnetic of the MHD, on the MHD viscosity of the turbulence. It's the time scale of the neutrino cooling. And simplifying a lot, what you have to imagine is that you have this system, it could be a disk, that basically tend to expand because there is turbulence and magnetic field pressure. But at the same time, it tends to contract because you have neutrino cooling. So you have all sorts of this kind of processes going on there. And if you calculate the time scale of these processes, they are all ordered from 100 milliseconds to seconds. And when I told that it's unclear, it's because it isn't clear.
No,
So
I think that's an interesting order of magnitude to have in your mind. I'm just thinking of the LIGO searches that have looked for hypermassive neutron stars with timescales much longer than that, but that's maybe a different scenario then.
Yeah, so
they're talking hundreds of seconds, thousands of seconds even for.
Yeah, if you go further, then you might enter again, a phase in which there is some gravitational wave instability, because you enter this window in which you might have, gravitational wave instability for rotating stars or so on. And that I think is what you are thinking, and it will be even longer, and might also overlap with this at some point, right? But the point that I try to make is that we really don't know. At the moment, we are unable to simulate with sufficient physics and with sufficient confidence and for sufficiently long time this type of systems. So we don't really know what what could happen. But in all of this, yes, there is also what you mentioned. So at some point, although it will not be, it might not necessarily be gravitational wave dominated, but there might be as well gravitational wave that are excited by some or triggered by some instabilities, or so on, some long-term instability of what is an almost equilibrium model.
Okay, so I'm afraid we must go on, otherwise we are too late. We are already 10 minutes late. So I'm sorry, Andrea, maybe you can ask to Sebastiano by chat your question. And I will go on to the next speaker, that is Simone Di Chiara, for the title of Search of Local Analogs of 170817 with Swift. So please, Simone.
Thank you. Can you hear me?
Yes, very well.
Sure. Thank you. So thank you very much. Thank you very much for organizing this session and for inviting me. And just for people that doesn't know me, I mean, I would like to introduce myself. I'm Simone Di Chiara. I'm a postdoc at University of Maryland and NASA Goddard. And today I'm going to talk about a bit about the search of short GRBs, analogs to 170817 with the Neil Garrett Swift Observatory. So since the beginning of its operative life in 2005, Swift observed more than 130 short GRBs. This is a large sample that allow us to characterize them in some way, to identify general features, to define a general paradigm, let's say. So in general, we know that short GRBs are characterized by a typical isotropic equivalent energy that is on average around 10 to the 51 ergs. And they are identified at different redshifts between 0.1 and the highest is 2.6. And they are characterized by afterglows that are bright at the beginning, and they rapidly fade after that. They have a quite steep decay after the first bright emission. We can see here the figure of a sample of X-ray afterglows of short GRBs detected observed by Swift XRT. You can see that the emission can be pretty bright. I mean, it can reach up to 10 to the -8 ergs per centimeter square per second, and they rapidly fade. I mean, some of them are more steep, some are less steep, but in general they are steeper. They fade more quickly with respect to the afterglow of long GRBs, for example. This paradigm was completely destroyed, revolutionized by the discovery of 1708, of the short GRB 1708-17. Besides providing the first direct connection between a short GRB and their progenitor, this discovery revealed the presence of a local population of short bursts observed off-axis. It was extremely near. It was discovered extremely nearby, as you know. It was at a distance of 40 megaparsec. That's extremely nearby. The redshift is 0.01, and this population of nearby short bursts is characterized by low luminosity of the prompt emission. The isotopic equivalent energy of this GRB was about 5 × 10⁴ erg. And the X-ray emission was become visible only several days after the GRB trigger in this case. So it was not very bright at the beginning, like we observed for other short GRB. And it became visible only several days after the trigger. And moreover, this event was associated with a peculiar kind of bright infrared and optical transit. We already saw the presentation of Sebastiano. We will have other presentations. So we know that it's associated with a kilonova signal, this emission produced by the radioactive decay of unstable nuclei produced by the neutron star capture air process that take place after the merge. But other people will talk about this. And I'm showing here on the left an image obtained by the Hubble Space Telescope of AT 2017 GFO, the point light source that is doomed. And inside the host galaxy, that is a typical late type galaxy, one natural question that rises after the discovery of 1708-17 is, was this a unique event? Have we ever observed something similar in the past? And studies of archival data reveal the presence of another short GRB with similar features of 1708-17, but it was discovered at cosmological distances with a redshift of 0.13. And this GRB is GRB 150101b. Also, in this case, the isotopic equivalent gamma ray energy it's low. It's one of the lowest measured for a Swift GRB. It's about 5⁻⁴ ergs. And also in this case, the X-ray emission was characterized by delayed onset. And we can see that it was localized in a galaxy, inside a galaxy that is very similar to the galaxy of 1708-17. And the analysis of the optical data for this GRB also revealed the presence of a possible kilonova similar to AT 2017 GFO, but a bit brighter than that. The study of the afterglow revealed that also for this GRB is an example of an off-axis event. Off-axis GRBs are characterized by afterglow emission that is orders of magnitude fainter than the one observed for the on-axis ones, and it shows typical delayed onset and late time peaks. As you can see here, I'm showing the light curve of the X-ray light curve of 1708-17, and together with the light curve of 150101b, that are the two events that we know were observed off-axis. And as you can notice, the off-axis emission will most likely be missed by the Swift XRT observations, which are more oriented to the detection of the early bright emission expected from on-axis events. So our work is oriented to answer the following question. Did we miss any nearby off-axis short GRB in the past? In order to address this issue, we considered the whole sample of short GRBs detected by Swift, but up to January 2019, and we selected the ones with duration less than 1 second, just to be sure that we are talking about short GRBs, ending up with a sample of 96 events. We then selected all the bursts with no afterglow emission detected by XRT in X-ray, as expected for the off-axis events, ending up with a total selected sample of 32 events. We noticed that for a fraction of them, actually, the lack of afterglow emission could be due to suboptimal condition at the moment of the XRT observations. For example, observations couldn't start immediately because it was because of the proximity of the sun, or because the trigger was disabled during the slew, and so there were these problems during the observation. So the afterglow emission was not detected probably for suboptimal conditions. So we identified a subsample that we call the gold sample, for which the GRB were observed in optimal condition. So the lack of afterglow detection indicate that the X-ray emission was actually must be particularly faint. In this figure, you can see the X-ray upper limits derived for the X-ray afterglows of the total sample of 32 events in black, and I also indicate in gold the limits obtained for the subsample of events observed in optimal conditions. So these limits are compared with the light curve of the on-axis short GRBs observed by Swift. You can notice immediately that they are the limits are very deep and are well below the typical values observed for the short GRB afterglows, especially for the gold sample. We searched for possible nearby off-axis events in our sample. In order to do that, we cross-matched the Swift BAT 90% localization region with a catalog of nearby galaxies. We used the GLADE catalog, focusing our search on galaxies at distance less than 200 megaparsec. And we found 4 possible matches. Okay, sorry, here. We found 4 possible matches. I'm showing here the 4 matches inside the BAT error regions. Zooming in, I mean, the 4 matches correspond to a percentage of about 12% of our sample. And this number is higher than the one expected from chance alignment. We ran different tests and simulation in order to estimate the chance alignment probability, finding that it should be about 3%, the percentage, the probability of chance alignment. So this high number of matches indicate that there could be a real possible connection between those nearby galaxies and our 4 GRBs. We see here in the figure the 4 possible galaxies zoomed in, and then you can notice that none of them is closer than 100 megaparsec. So we did not find any event a similar distance of 170817, which was at a distance of 40 megaparsec, so extremely nearby. So we didn't find anything similar to that. All of them are between 100 and 200 megaparsec. And just for 080121, we found 2 galaxies, 2 nearby galaxies inside the BAT error region, you can see. Here, you can see the light curve of the prompt emission of the 4 short GRBs nearby short GRB candidates, together with the observed gamma ray isotopic equivalent energy derived, assuming that each burst occurs inside the putative host galaxy. As you can see, the values of the isotopic equivalent energy range between 10 to the 46, 10 to the 47 ergs. These values are very similar to the one observed for 170817. And so the energetic, at least, is similar to the one expected from an off-axis GRB. We then searched whether any of these four bursts was associated with a kilonova. Unfortunately, no infrared sensitive observations are available to constrain the emission of the red emission of kilonova for this case. So we use the optical limits derived from different telescopes, using the observation taken the days after the GRB detection in order to constrain the kilonova properties and derived information about, for example, the mass of the ejecta or the velocity of the ejecta. In this figure, you can see that the optical limits in absolute magnitude you can see that they are below the emission expected from AT 2017 GFO. You can see a downward triangle and downward arrows indicate the limits derived in the internal and external regions of the galaxies, respectively. As you can see, yeah, we can rule out the presence of a bright kilonova such as AT 2017 GFO, and which was associated with 170817. And let's remember that this GRB was observed with an off-axis angle of about 25 degrees. But we cannot exclude fainter events. For example, we cannot exclude events similar kilonova, a kilonova similar to AT 2017 GFO, but observed with at higher latitudes. For example, here I'm showing the light curve of a kilonova similar to AT 2017 GFO, but observed with an off-axis angle of 60 degrees. It is good to note also that we are less sensitive in the central region of the galaxies. Indeed, the GRB, if the GRB is located close to the galaxy center, the identification of a kilonova becomes more difficult. In this plot, I'm just showing the constraint obtained for using our optical limits in the internal region of the galaxy for the ejecta velocity and the ejecta mass, considering a lanthanide poor ejecta, only considering a lanthanide poor ejecta, so the so-called blue kilonova. The gray region is the part of the parameter space that is not allowed by our upper limit. As you can see, if, an ejecta velocity lower than 0.3 of the speed of light is allowed only for ejecta masses less than 10 to the 3 solar masses. These values are very different with respect to the ones observed for 170817 and could suggest a quite different environment, for example. We then use our result in order to derive the whole sky rate of short GRBs, finding a rate of about 160 events per gigaparsec per year. This is equivalent to a number of detectable local short GRBs of 0.16 events per year with Swift and 0.8 events per year with Fermi. These numbers are associated with a large uncertainty. You can see the dark orange region in the figure is the 1 sigma error. This uncertainty is due to the low number of local short GRB candidates identified in our search. As you can see also from the figure, the rate is much higher. This rate is much higher than the one derived from the observation of cosmological short GRBs, and is comparable with the rate of binary intra-star mergers derived from gravitational waves observation of advanced LIGO and Virgo during the O3 run. This result suggests that the local population of short GRBs is probably dominated by low luminosity events that are likely to be observed off-axis, while cosmological observations are biased in favor of more luminous on-axis events. Also, comparing the two rates, the rates of gravitational wave, binary intra-star mergers, and the rate of short GRB, we constrain the beaming factor of the emission to be less than 20. Okay, in conclusion, we did not find any evidence for a large population of short GRBs observed off-axis in the local universe. In particular, we did not find any event similar to 170817. This suggests that this kind of event is not frequent. To summarize, we find just 4 possible candidates at distance less than 200 megaparsec. Assuming that they are actual nearby short GRBs, we derive the all-sky rate, an all-sky rate of about 160 events per gigaparsec per year, which means a detectable rate of 0.16 events per year with Swift and 0.8 events per year with Fermi. So this suggests that the number of common detection between short gamma bursts and gravitational wave will increase probably slowly in the future. We also use that these results to derive information about the collimation of the jet, finding that the beaming factor should be less than 20. Also from the study of the optical images, we did not find any evidence of a 1708-17 kilonova. The derived limits help us to put constraint on the ejecta mass and the velocity of a lanternide poor kilonova, although we cannot exclude the presence of a possible lanternide rich kilonova due to the lack of the infrared limits. In conclusion, I want to stress the point that an optimization of the follow-up strategies and a systematic search of sub-threshold untriggered bursts with sensitive wide field GRB monitors in the future would be crucial in order to increase the detection rate of off-axis short GRBs and to better estimate the rate of short GRBs in general.
Okay, thank you. Thank you very much, Simone, for also being perfect in time. So there is time for a few questions. So I have a question. In fact, are you considering to implement in your analysis also, because I see that you have put a filter to the selection of the sample you have analyzed to all the short gamma bursts of Swift that have a duration less than 1 second, while in several cases we know that there are many short gamma bursts that are longer than 1 second, but they have clear properties belonging to the short gamma burst class. So I'm wondering if we may have missed some very faint short gamma bursts a bit longer than 1 second, and if you are considering to extend your analysis also including this other short gamma bursts.
That's a good question. Thank you, Julia. I mean, let me just explain very quickly why I decided to put this selection to 1 second. I mean, everything starts from a work of Bromberg of 2013, in which he explained the probability of being a non-collapsar, we say, for different, considering the different instruments. So the probability of being a short, having a T90 of 1 second for Swift is different of the probability of being a short, having a T90 of 1 second with Fermi. I mean, from this analysis, it's explained that about 50%, you have a probability higher than 50% of being a short only if you take T90 less than 1 second. That's why I choose that time. But it's definitely a good idea to try extend this up to 2 seconds and see if we find something something interesting. For example, up to 2 seconds. Well, above 2 seconds, it would be very likely that the GRB is actually alone. But up to, I can extend the analysis up to 2 seconds, definitely, and see if I find something interesting. Indeed, yeah, you're right.
Okay, thanks. So, are there any questions for Simone? Okay, so if not, we can proceed. And the next speaker is Andrea Rossi. He will talk us about the kilonova emission observed so far and a comparison with AT 2017 GFO. Please go on, Andrea.
Thank you, Julia. And I'd like to thank the organizer for inviting me to have this talk. So, yeah, so we'll talk about the kilonova emission observed so far and comparison with AT 2017 GFO. And in particular, I will first talk about the kilonova associated with gravitational waves and short gamma burst, and the comparison between short gamma burst and the optical near infrared counterparts with the AT 2017 GFO. I will use this comparison to obtain constraints on the kilonova luminosity, and will try to show some future perspectives on the follow-up of kilonova in the near and future in the 30s. So follow-up of gravitational waves is not an easy game. So when we have a gravitational wave candidate from LIGO, Virgo, and so from CAGRA, we obtain these sky maps, as you can see here, and very large sky maps. And we have to start to decide which is the best observational strategy to follow, to cover these sky maps. But we wait a little bit because we have to wait for the event validation. So, and usually this takes 15-30 minutes. Before we want to wait for this, of course, because we are going to activate the biggest facilities in the world. So, okay, if you have a small telescope, perhaps it's not, you can activate after everything. But if you're going to activate the 10-meter telescope or 4 or 2-meter telescope, is also with a large field of view, is you have to be careful. So in 15-30 minutes, we are quite sure from our friends flying Virgo that this is not terrestrial noise. And then we can start with the follow-up, especially first with the search for the kilonova counterpart. And when we find the counterpart, this can be characterized from the big telescope, the big glasses like VLT or LBT here in Arizona. This is showing the facilities we are mostly using within the Italian follow-up collaboration Gravita. Here we have TNG and VST, and this is on the bottom left. This you can see how to cover a typical sky map of LIGO and Virgo with the 1 square degree field of views of VST. So this is for search for the candidate, and the first characterization is then we have also part of ENGRAVE, which is fully devoted to characterization of the counterparts. It uses ISO facilities, especially VLT. We have also program with ALMA. I mean, not only optical, also access to ALMA, and proposal running for HST. Includes over 250 researchers with both theoretical and observational expertise. This is very nice. Where it's a place where we can exchange ideas and also help each other with the follow-up. Usually also small telescopes that are not included in VLT. It's really a nice place where to organize the follow-up. So ENGRAVE was not still really active when this event 1708-17 happened. This like we call it 3-in-1 event, where we have a short gamma burst, the first electromagnetic counterpart. Then this is the first time they show evidence of the nature of short gamma burst, so the merge of 2 objects, and is the first spectroscopic kilonova in 2004. You know this famous picture with the kilonova discovered within the aero region of LIGO and Virgo and the Fermi GBM aero region, and this is discovered by the SWAP telescope in this galaxy at 40 megaparsec, which is not there in the image 20 days before. So this is 4 years ago. Then we didn't have really any other counterpart from BNS event. Of course, although there was another BNS event followed up by discovered by LIGO Virgo. But this last week, you probably heard about the neutron star black hole events, the first confirmed neutron star black hole events, and I just grabbed this nice plot from their paper, like the Virgo paper, paper, showing that the mass of the smaller the lighter component is below 2.5 solar masses, and this is the first event confirmed that the smallest, the lighter component star is a neutron star. So, do we have electromagnetic counterparts for this? The answer is no, and the reason is that one event was unfortunately didn't have a very small sky map area, as you can see on the bottom right. Okay, we have to look for event in all this region, and also, although the other event was in a smaller region, this is has a very bad observability in January when this event happened. So you can see a little bit this region, but probably not at all from ground. You can see that from this region. So you have the sun not helping you in this game. And so there is a paper from ZTF, Natural Astronomy, saying that they could cover 50% of the coverage, but I mean these are even at 300 megaparsec, and ZTF is not likely enough to put big constraints on this on the luminosity on the kilonova. So here in this plot is also showing 1908 to 14 and another event 1904 to 56. They are both have I mean one event is very similar to 2115, although it's very low probability to be real. The other event is up here. It has a very lighter mass. Event is very high, and it's not very clear. This is really a neutron star, only very stable. Although Engrave tried to, I mean, the event has a very small localization here, so we could do a very good work in trying to we could cover very well, both with targeting just the galaxies they are in the map, or just a very deep coverage of all the area. And thanks to the limits, they were able to put covering some days up to 90% of all the area. We could put deep limits on the possible kilonova associated with this event, and 95% we can say that there was no event with a total mass smaller than 0.1 solar mass. This is the basic. So this is everything for kilonova associated to gravitational waves. But as you know, as I said before, 170817 was associated to a short gamma ray burst. It's also nicely shown by Simone. And so in the sketch on the right for this kilonova, you see what happened. You have the kilonova coming from the merger of the two neutron star, but this also produces a jet, and then leads to an afterglow that becomes visible later when the jet opening angle is large enough to the decreasing of the Lorentz factor, and becomes later visible in the scale radio. So we can look for a kilonova associated to short gamma ray bursts. And yeah, I want to show, this is a big map of all the known kilonova. On the left, top left, you have the AT2016 associated with gravitational wave and gamma ray burst. It's the only one with the spectroscopic follow-up. This is very important. All the others have been detected with just photometrically. There are, you can see, at least 7. Recently was proposed this event by team of Fang, but there is another paper saying that maybe this is not a real kilonova. There are some other events. This of 7829, and there is another known kilonova, but there is no possible association to any redshift. So most of kilonova we know are from short gamma ray bursts. And so the idea is, if you want to study kilonova, up to now we have to study kilonova associated to short gamma ray bursts. But so we decided to use the information to use the light curve, optical and near-infrared light curve associated to the counterparts of gamma ray burst to see what we can learn. So what happened typically for the short gamma ray burst with the kilonova, here we have 130603b. You have the kilonova, the afterglow is very bright at the beginning, is dominating over any kilonova light, and the kilonova becomes only visible. Of course, this is valid when the object is the GRB is on axis. One becomes only visible when the near infrared component becomes dominant, peaking later. And in this case, this was confirmed to be a kilonova thanks to this deep upper limit, because otherwise one can also suspect this to be a supernova, but the supernova can only evolve much lower. So it's possible we have to be careful to the afterglow, but it's possible to put constraints on the luminosity of kilonova using short light curve of the afterglow short gamma ray burst. So this is the work we did. We selected 39 short gamma ray bursts, redshift up to 2.2. Basically all short gamma ray bursts with no redshift until 2018. We started from a sample of a paper from Franck, and everything was updated with literature. And within this 39, 29 only have a well-defined redshift. Determining the redshift for a short gamma ray burst is not very easy, because usually they all come from the host associated to the gamma ray burst. And it's not very easy to be sure which host associated to a short gamma ray burst. So to do this study, we compare the afterglows of gamma ray burst with a sample of template light curves we built from the spectroscopy of AT2017 J4. The work started from Elena, and we use this with the spectroscopy to build this light curve that you can see on the right in the rest frame of the gamma ray burst. And this is 130603b from the show before, and this is the detection H band, okay, compared to these are light curves of the kilonova. This is the only study I think that could build light curves from the spectroscopy of AT2017 J4. So we use this to show a ratio of the luminosity compared to of the optical and near infrared afterglow of the gamma ray burst compared to AT2017 J4. So this is a ratio of the blue component, okay, the optical peak compared to the luminosity of the AT2017 J4, which is of course this line. So we first find, if we concentrate just to the 7 GRBs which have a claimed kilonova, which are all these with a circle, we found that most of them have a luminosity which is comparable to AT2017, more or less than 3 times, which are all here, most of them. Then there are there are 2 peculiar events, 060614, and up here, which is more than 100 times brighter than our kilonova, so 7 or 714 is just 1 point. Then perhaps there are events we found that have a very shallow evolution, but it's difficult to confirm if this can be a kilonova because there are just few points, 1 in this case and 2 in the other. and also the redshift is quite uncertain. And then we found events with a certain redshift for which there is no emission like 82017 GFO associated. So this is, if the kilonova was here, it might be faint. So then we use all these constraints on luminosity later to build a range of luminosity versus redshift. But first I show you here the same work we did in the red. This is red, I mean, is the rest frame near infrared. And here, in the same way, you see there are a lot less points. There are just 3 famous kilonova, 160821b, which is less fainter than our nice example, 2017, or 5077 or 5079, which is basically the same. And the first kilonova, famous kilonova, is much brighter, but just 3 times, sorry, 3 times brighter than our kilonova. So in near infrared, they look much more similar, but we have just 3 examples. We have to concentrate just on this part because this part is basically probably dominated in the near infrared by the afterglow. So it's for the infrared, we concentrate on the after 2 days. Also where the near infrared is expected to peak. So this is the big summary of this luminosity constraint. We have a large range of blue luminosity here, and this much smaller range on near infrared component, although we just have 3 examples. So this is the slide I showed before. The only difference is that I highlighted here those that are probably 10 times brighter in the blue. This new, which I added later after this study was done, 2018. We have this guy from paper from Gao, and maybe also these 2 which are marginally brighter. I mean, they are on the limit to be more than 10 times brighter than our famous kilonova. Then we have possible new candidates here, although not very well sampled, with a certain redshift. This is, I think, is the everything is known about possible kilonova associated to Shogun burst and gravitational wave signals. So if I have a few minutes more, I don't know how many minutes I have.
5 minutes.
Okay, thank you. So in the next minutes, I want to show what is possible to do in the future. So this is our
3 minutes.
3 minutes. Okay, we'll be quick. So in the future, in 0405, the BNS range of gravitational wave signals will increase, time to LIGO and Kagra, and will also be 2-3 times larger than now. So here on the right, I show the limits in redshift with this line of 404 or 5 of the BNS range. And here is the peak luminosity in the blue from the constraints I just obtained. So this blue line is our famous kilonova, 82017 GFO, and these are the range down to 0.5 up to roughly 10 times brighter. Okay, so what this plot wants to show is that spectroscopy, so characterization of what is this transit to decide if this is a kilonova or not, is not a problem. I mean, when you find a candidate, you can activate a 10-meter telescope and take spectroscopy very easy of something that is up here at brightness during 04 and 05. The problem is to localize this event, because if they have hundreds of thousands of square degrees, surveys have a lot of work to do, and the surveys based on smaller telescope can arrive up to here, and fainter event can be easily, I mean, this is in the optimal condition, can arrive down to 21 magnitudes, but you need bigger facilities like Vera Rubin, or for example, we have the BST, TISO, to go deep enough and to be sure to detect these sources. And then the characterization can start. The future, we will have the 30s, the third generation of gravitational wave observatories like Einstein's telescope, called Cosmic Explorer. I will concentrate on the Einstein telescope. So the bulk of the BNS events will be a redshift below 0.5, but for the majority of these events here, they will have a localization larger of 1000 degrees, or in any case, much larger than 100 degrees, okay? All this area here. Only for the very close events, okay, here, you have the localization small enough that is very easy, quite easy to find a kilonova candidate identified with characterization. So going back here, this is the bulk of by Einstein telescope events. You have the thing optical. I mean, even for the, or just for the brighter event, spectroscopy can find can characterize kilonova. Otherwise, from a 10 meters telescope, there is no way one can. I mean, it's very difficult to go deep enough and have a good characterization of the transit. This will be a big problem for redshift larger than 1.2. So all these events here will have a big problem to be, even if you find the candidate, we'll have a big problem to understand what it is to characterize. So the biggest telescope facilities like JWST and the LT will work in the, especially in the infrared, they work here. So if the BNS events, the book of BNS events will be a redshift below 0.5, therefore here. So you can see the spectroscopic characterization will be maybe easier for these big glasses up to redshift of 0.5 still, but becomes a bit problematic. Okay, the problem is still that the surveys in the infrared can go very deep. Okay, but even if we forget the surveys, the problem is that even in just in the cases that are much brighter, JWST and ELT can help up to redshift of 0.5. So we can have just the question is if we will be able to find and characterize all the kilonova associated to the best localized gravitational wave. Okay, a redshift 4.5, redshift 4.4, it can be very difficult. Okay, this is, I mean, this limit I put here is probably true only if certain conditions can be used. Like you can also use adaptive optics observation. Otherwise, it's very hard. And the redshift is very important, as you know, also to compare with the luminosity distance for gravitational waves, also to put constraints on the Hubble constant independently from what is done up to now. A solution can come if there is a space gamma observatory dedicated to gamma ray bursts, because as I showed before, gamma ray bursts and thereafter are much brighter at the beginning. So one can, if there is a on-axis event, can be detected gravitational wave, can be detected by the space observatory. And then a small telescope can follow up the afterglow. There is plenty of information of the afterglow, and then bigger telescope can concentrate on these few events that have gravitational waves plus gamma ray burst associated, and can go deep enough to do spectroscopy. Maybe this the limit I put here is I think 1 hour, but if there are not many events, you are already a very well-studied afterglow, will follow at maybe that for the meter telescope, or ELT, also some photometric point is easier to spend more time to this event and go much deeper. Go much deeper. Or otherwise, you can also get a redshift from the Earth galaxy. So, as I said before, it's not easy to get. It's the lossless problem for short gamma ray bursts. It's not always easy to associate a short gamma ray burst to a host. Similar to conclusion, also were reached by another paper from very recently, and here they show here on the right how deep they can go. They are now the upper limits obtained up to now of observation of all short gamma ray bursts. And you can see that in infrared, these are models of kilonova, a ratio of 0.2 to 3.5. The upper limits we are typically obtaining are not deep enough from ground observation, are not deep enough to put limits of kilonova, a redshift above 0.2. Okay, so the only in the left, you saw basically it's the same. You have the redshift, you have the time, and here's the going to light region. Here is the limit of ground telescope. Here is a, for example, 2017 G4, I think a redshift of 0.15. And if you move up this, only this line gives the upper limits from a space observer, from a space from JWST or from ELT. They only one can provide follow-up for events that redshift up to 0.4 or 0.5. So this is my summary. To end, most kilonova are associated to short gamma ray burst, although, as I show here, this plot, 28% of all short gamma ray bursts cannot be compared to our kilonova, ET 2017 GF4, simply because the time of this observation is too early. Most observation is too early. In other case, the afterglow is dominated. The majority, 40% of most of cases are dominated by the afterglow. Although we could put upper limits in 2 cases, finding that if the kilonova was associated with this gamma ray burst was fainter than ET 2017 GF4. It's also interesting that the optical, the blue part, the rest frame blue part, as can be brighter than ET 2017 GF4 up to 10 or more times brighter. Although the near infrared is much more similar, around 3 times more or less brighter than our kilonova. But they are just 3 events. Although I think it's interesting that aspect that what can come from dynamical ejecta as more consistent in luminosity. Future perspectives, we need more near infrared kilonova, so which means that we need more observation in these bands, deeper observation, especially in the future, in the 30s. The JWST LT will probably be the only ones can reach a kilonova at redshift beyond what we can find kilonova now, so be up to redshift 0.5, where the bulk of kilonova, the bulk of the gravitational wave events will be found. And I stop here. Thank you.
Thank you, Andrea, very much. It's a very nice review of all the observation of kilonova. We have not time, but if you have a very quick question, you can go on to Andrea. Okay, so if there are no questions, I move on because we are still very late. And the next speaker is Elena Pian, and she will talk us about kilonova ET 2017 GF4, and in particular on the evidence of heavy air process elements. So please, Elena, go on.
Yeah, okay, thank you very much, Julia. Thanks for this invitation. So I will try to elucidate a little bit how much have we learned from these spectra, from the spectra of this single event, and especially what real evidence we have that our process elements are in those spectra. Do we really see our process elements? Well, the problem is historically, as soon, almost immediately after the detection of the first binary neutron star, the binary pulsar in '74, there has been discussion, there has been speculation that the mergers, the final phase of these systems, meaning the final merger of these 2 neutron stars, should lead unavoidably and unequivocally to our process nucleosynthesis, just because of the uniqueness of these systems. It's virtually the only places in the universe where you can have these huge neutron densities and huge energy densities that are necessary for this extremely powerful nucleosynthesis. There are many papers that put this in a theoretical, in a quantitative way, and make predictions, starting, for example, with the Schramm papers, Simbalisti and Schramm, Latimer and Schramm. there is the first paper that explores in a detailed way, in a pioneering, but rather detailed way, the conditions for free neutrons deconfinement after neutron star merger, is this seminal paper by Freiburg-Haus in 1999 that explores the temperature, constructs this temperature versus neutron number density in the very first milliseconds after the merger, and explores the fractions, the relative fractions of neutrons that can be made available at these phases, and tries to isolate, tries to confine the region in this parameter space, in this temperature density parameter area, the region where the R process can occur. And it is as you see that the neutron number densities are significant immediately after merger, significantly lower than in neutron stars themselves, but are still the highest neutron densities you can find in nature, in any explosion, including supernova. Up to the detection, until the detection of the first binary neutron star merger, the optimal candidate, the top candidate for R process as an R process site was thought to be core collapse supernovae. And although it was widely known, widely accepted and admitted that it was difficult to make the conditions of energy and density, neutron densities, sufficiently high for our process. So supernova appeared a possible, still is a possible R process site. There is still R process nucleosynthesis in supernova, but it is probably not dominant. More recently, it has been investigated if jet is the most powerful part of the supernova, meaning relativistic jets. So we are confining the exploration to that small fraction of supernovae where jets relativistic powerful jets can be produced. Can those be sites of our process? Well, maybe, but these events are very few, are maybe 1,000. We know that for long gamma ray burst statistics, that these events are not, relatively speaking, relatively to the core collapse supernova population, are not dominant, are a very small minority, are a rarity. And there is a further problem with jet supernova models as our process sites. When 3D simulations of core collapse have been developed fully, it has been discovered that in 3D, there is an effect that in 2D is not apparent. It doesn't surface, but in 3D you see it. It has been discovered that core collapse is much slower than one thought before, just based on 2D simulations, because jets in 3D develop a kink instability and make the whole process of jet formation and launching much slower and more inefficient for what concerns our process elements production. Lately, there has been a proposal that not the jets, but accretion disks of collapsers, namely the disk that forms promptly around the newly born black hole after collapsal, those sites, those regions can host our process. There is this rather popular Siegel et al. Nature paper in 2019. The problem with that prediction is that it is very difficult to test it observationally. The diagnostics, there are some diagnostics in the paper. Actually, if you read the paper, if you confront the authors, if you talk about the real range of predictions that paper leads to, it's much more diverse, much wider than just the scheme in the paper indicates, and therefore it's very difficult to compare these realistic predictions with observations, just because the prediction has is too diverse, has a too wide extension of parameters. So supernova as an process, core collapse supernova, be it the core, the jet, or the accretion disk in collapsar, is a rather problematic site for our process, which brings back binary neutron star merger as the most straightforward, the most realistic and viable model for our process. The question is, can we, in this single observed example that we have, a very well observed example that we have now, can we identify a clear evidence? Well, looking at the light curves are very similar to supernova. They are dimmer, they are faster than supernova, but they are qualitatively very similar, meaning they indicate clearly that there is these sources, the ultraviolet to infrared light is thermal light of radioactive origin. It has, this is the typical, see these fast declining, exponentially declining sources indicate evidence that this is a thermal source of radioactive origin. The compounding circumstance is that while in supernova, there is one species that dominates the radioactive decay, which is nickel 56. In the present case, these light curves are the convolution, result from an envelope. They are convolution of many radioactive decays of different E-folding times, many different E-folding times of many unstable isotopes. Therefore, we focus on the spectra. We try to see if we can find more evidence from the spectra. The spectra are, what do the spectra tell us? Well, the first thing these spectra have indicated is that, like highly energetic supernovae, one observes broad absorption lines. The absorption lines that one expects from these sources are not narrow, but broadened and blue shifted as expected from a medium that, a photosphere that expands extremely rapidly and generates a very strong aberration by the effect, by the deformation, the broadening of the P Cygni effect. So which I will show in a moment. So the most important, the basic difficulty, the primary basic difficulty in interpreting these spectra is the extremely large amount of lines that one sees and one expects. If our process is really taking place, if in this site really elements are formed, all elements are formed with atomic number higher than iron, you expect not only a lot of elements. If you look at the periodic table, you see it immediately, all the elements higher, more heavier than iron should be produced, up to lead and bismuth should be produced, and including the lanthanides and possibly actinides. So you expect these elements not only are many, are intrinsically very numerous, but they are having such a high atomic number, they have an enormity of levels, an enormous number of transitions. Therefore, you don't expect, like in supernova, light, more or less light elements with some favorite transitions that you can train yourself to identify, to recognize, and you can compare with line lists of light elements. Like, for example, this is the famous supernova 98 BW, the prototype of the progenitor of long gamma ray bursts. These are spectra taken at different epochs after explosion. And you see here a series of lines with which the observed absorption lines have been identified. And this is right now, currently, regularly, routinely done for supernovae. The elements are rather well known: calcium, titanium, chromium, iron, silicon, oxygen, calcium. The transitions of these elements and their atomic opacities are known rather well, and you can, once you know them, you can predict rather easily what will their appearance be, and you can identify them on the spectra. We don't have that luxury in kilonova, because you see very few of those light elements. Most of the elements are very, very heavy. So that's the first difficulty. The second difficulty is this P Cygni aberration that I was mentioning, meaning this is the classical scenario in which you are observing, which is characterizing kilonova and supernova. This is the same. You have an expanding explosion, an expanding object, an expanding photosphere that you observe from a certain direction. So what you perceive is absorption lines due to elements, the elements in the atmosphere, in the circum explosion medium. These elements imprint absorption lines that form, that give this characteristic, have this characteristic shape. An absorption line on the blue side and a scattering, a reprocessing emission component redward of that absorption feature. That's not an emission line. It is, well, it is, but it's not a recombination line. It is a scattering line where all of the blue photons that have been absorbed are re-emitting their light, their absorbed light. So this is the typical P Cygni profile in a star, for example, very easily recognizable. In supernova and in kilonova, these profiles are blue shifted. You see it again very well in 98 BW, where you see here the profile of a typical silicon 2 line, typical line of core collapse supernova. The P Cygni profile of silicon 2 is blue shifted. The bottom, the minimum of the line is not at the laboratory wavelength where you expect it to be, meaning 6355 angstrom, but it's blue shifted with respect to that wavelength. So the line, the absorption line is broadened, the profile of the line is broadened and blue shifted. The blue shift is a function of time. The line is, as the photosphere recedes and the ejecta slow down, the blue shift is less and less. And eventually in the latest spectrum, there is no blue shift, almost no appreciable blue shift anymore. You see here on the right, the profile of the blue shift, the same line, the velocity of the line that is decreasing and finally getting very close to the to velocity zero, meaning the line is finally seen at the laboratory line, modulo the cosmological correction, the cosmological redshift correction. So once you put all of these effects together, blue shift and broadening, you have a typical spectrum here in what you see here in broad-lined 1C supernovae. This is a typical spectrum of gamma ray burst supernovae, for example, a very a spectrum dominated by broad lines, where each species suffers this effect. Each atomic absorption line, each atomic transition suffers this effect. So the lines tend to blend with one another. Unlike in narrow-lined supernovae, for example, on top in black, you see a narrow-lined 2B supernova, narrow-lined in blue, narrow-lined 1C supernova. The lines are narrower and much better visible. All of these lines, because of the high velocities, are blend together and blue shifted, and it is much more difficult to recognize them, to isolate and identify them. And this is what happens in kilonova, which makes it difficult, which compounds the identification. So So in general, what the general knowledge, what we knew before, just before the event, and what we tried to, the information we tried to use to interpret in the first epochs after the event, the information, the general scheme, general picture that one has used is this two-component behavior, two-component geometry that has been discussed before during this session. One more rich in neutrons, more lanthanide rich. Lanthanides are represent, as we've seen before in the periodic table, all the 14 elements, starting with atomic number 57. They represent the so-called F block group of the periodic table, and are characterized by a huge number of transitions with very small energy differences, one with respect to the other. So they have many transitions that generate big opacities, and therefore are expected to blend, to suppress the blue part of the spectrum in a dramatic way. So if they are produced in big numbers in the dynamical ejecta, meaning the ejecta that are immediately formed, the polar, the equatorial-like ejecta that are immediately formed, they they suppress the spectrum of this component in the blue part very much. So you expect a very red component. And on the other hand, this more polar component, if there is a metastable object that forms promptly, like a hypermassive neutron star, this before it decays into a black hole, this hypermassive neutron star presumably producing a cooling MEV neutrino wind that thwarts, inhibits the formation of more neutron-rich elements, and therefore the elements, the atoms you see in this neutrino wind are more poor in neutrons, and therefore more poor in lanthanides, and they produce a more blue, a less suppressed spectrum, a more blue, blue-like spectrum. So this was the expectation. There was no hope, no delusion of being able to identify any individual species, and that's exactly that paradigm is exactly what we followed in the first pioneering modeling of the source that we have proposed. Lanthanide rich equatorial dynamical ejecta component, rich in neutrons, and two wind component, two polar components, wind-like. One is more isotropic, the other is more collimated, and they are both poor in lanthanides. And these are the spectrum we came, the spectral models we came up with. The black lines here, the black curves here represent the observed spectra during the first four initial epochs. In color, orange, green, and blue, you see the three components that we have hypothesized, and the convolution of these three, so the three models for the three separate components, and the dark red, the marked red solid line is the convolution of these three models. And as you see, it provides a decent job at the beginning in the first spectrum at 1.5 days, and it's poorer and poorer at subsequent epochs. As time goes by, the model seems to produce worse, an increasingly worse spectrum, which is essentially due to the effects I was mentioning, meaning we are not sure at all that we have considered the correct, we have taken a solar-like abundance distribution. At 40 megaparsecs, it is a relatively reasonable assumption, but we are not sure that our relative abundances we have hypothesized, we have put in as an ingredient, are the right ones. We are not sure. We probably have taken into account the blue shift in a more or less correct way. We have no way of knowing how much the blue shift is. We can only estimate it. We have estimated it to be like between 20 and 30% of the velocity of light, and we hope it is correct. That's what everybody is doing, more or less. But the most important hurdle in reproducing these spectra is that whatever abundances, whatever atomic species and abundances thereof we can think of, we can put in as an ingredient in this model, we have almost no idea of what their opacity is, meaning we don't know, we are almost completely ignorant about the effect of these, which effect these atomic abundances will have on the spectrum, how much they will absorb the light, the continuum. So 2 years after our initial paper, after these observations and modeling, we have tried a bit harder to detect, to find if we could, to interpret a little bit, to give it a bit more thought, look at these absorption lines in a little bit better way and see if we could interpret them, if we could at least get some better clue. And a better clue has come from the detection, from the comparison of our spectra with the lightest R-process elements. In particular, that we have noticed that the first spectrum, which is almost a perfect black body, in reality deviates from the black body in two prominent ways, around 35 angstrom and around 8100 angstrom. And we have started from these two deviations. If these two absorption features are blue shifted about 20%, with about 20% of the velocity of light, what would they be in the laboratory? Those two features in the laboratory would have these two wavelengths that you see here, about 4,000 and about 10,000 angstrom. And we, in the line lists of the lighter R-process elements, these two correspond to a very specific transition corresponding to the strontium, to the two transitions of the strontium once ionized, SR2. So this is an SR2 optical line, and 10,300 angstrom is an SR2 triplet. And they seem to fit the spectrum quite well, quite satisfactorily. We have done a test with 3 possible abundance distributions. We have taken a purely solar abundance, R-process elements with purely solar abundance distributions, as you see here, the continuous blue line. And we have taken 2 stars, the green and the red symbols. In particular, 2 stars that are relatively metal poor. And we have elaborated the spectra of these in these 3 situations, putting in solar R-process, all R-process elements, solar R-process elements. Then we have tried with the strontium only, you see it in red dashed, and in blue you see R-process elements, but excluding strontium and barium and the lanthanides. And it's only the red light here. It's only with strontium that we can reproduce the observed spectra in a satisfactory way. A circumstance that reinforces our belief that what we observe here is really that line, is really strontium, is that strontium represents the peak of the S process, slow process abundance distributions and is relatively high, relatively close to the peak of the the first peak of the R process abundance distributions. So you expect, of course, the peaks of these distributions that you see here, bottom left. These are abundances as a function of mass number. How do the peaks occur in these abundance distributions? Well, the peaks of these distributions represent elements, atoms, that have particularly high nucleonic binding energies. So these are species that are more stable, and therefore, being more stable, are more frequent, are more abundant, and they form peaks in these distributions, maxima. So the fact that our candidate species belongs to a maximum, both in S process and R process, reinforces our belief, our persuasion that we have actually identified the line correctly, because this line has a high probability of being seen, of being there. This species is highly probable.
Sorry, we have to conclude because we are late.
Yes, actually, I am at my summary. So my conclusion is, we don't have evidence, we don't have proof that we have identified our process elements. It's just very highly evident. There are big problems in identifying individual lines, which I have described. The biggest problem being knowledge, reaching a good knowledge, which at the moment is almost inexistent, good knowledge of the atomic opacities. We have a tentative identification with one R process, with an element which is actually produced both by R process and S process. The state of the art in the production of model atomic structure, correct model atomic structures and opacities is good. There are several publications, several papers that have proposed atomic structures and atomic opacities. The subsequent step is to benchmark, to prove these opacities experimentally, meaning in the laboratory, with, for example, with laser-produced plasmas. This operation has not been, is matter of ongoing research, has not been done yet. So I will leave, thank you for your attention. I will leave it here.
Thank you very much, Elena. This very exhaustive and clear talk. Unfortunately, we have no time for questions, but if you encourage all the people who would like to make some questions to Elena to put them in the chat, and so also that everybody can read them.
Okay.
And sorry for this, but I'm not sure about the time we have after the end of this meeting. So I'm afraid they will close the Zoom session.
Yeah, I think so.
So we going on, and the next speaker is Brigitta Hajala, and the title is A New Source of X-ray in GW17017, 3.4 years after the mergers. So please go on, Brigitta.
Can you see my slides and the cursor?
Perfectly, yes.
Okay, thank you so much. Hello, everyone, and good morning from Chicago. I am Brigitta Hajala, and I'm at the end of my 4th year in PhD. And first of all, just thank you, Julia, for inviting me, and Marika for inviting me to give a talk here. And as Julia said, I'm going to be talking about a new source of X-rays in GW17017, 3.4 years after the merger, or is there any new source? Okay, so we already have heard so much about the first evers of GW17017. You know, it was the first detection of a gravitational wave source from a binary neutron star merger, the first EM counterpart, the first observational evidence of a kilonova, and all those firsts. On the property side, we should basically focus on moving on from the thermal emission part of the session. Now I'll be talking about the non-thermal emission from GW17.17 and what's happening right now. So it's at a distance of 40 megaparsecs, which is really, really great for us because it's so close that we can still observe emission from it right now. The gamma rays, they were detected 2 seconds after the gravitational wave trigger. As previously said, in the optical, we've already heard that the blue kilonova peaked around a day or so, and then it faded away. The red kilonova peaked around 5 days, and then it faded away. So at early times, optical and UV and these wavelengths were dominated by the thermal emission from the kilonova. But at later times, non-thermal emission of the jet afterglow, it appeared, and it started dominating it. The X-rays, we did not see any emission in the X-rays for the first 9 days or in the radio for the first 16 days. So all of these properties, they had like implication of what was going on. There was a lot of speculation because it's the first time of almost everything. No one really knew what was actually happening, but finally the community converged onto one model that could explain the non-thermal emission in X-rays and radio. And that is explained by that there is a jet. So the jet, it was launched and it's successfully made through the merger ejecta. And the jet has a structure, but we are viewing it at an angle. So therefore we didn't observe any X-rays and radio for like the first few days. And the jet, we could, with all the observations which we had, we could constrain the angle of the jet to 2 to 4 degrees and the viewing angle to like 15 to 25 degrees. The energetics of the jet, most of the system parameters cannot be constrained because it is so highly degenerate, like the whole parameter space, and we do not have enough constraints to properly like individually constrain this. So especially the kinetic energy of the jet and the density. But we can constrain the ratio of it, which we constrain it as like 1 × 10⁵ erg per centimeter cube. And in this picture, like this is the jet, and the non-thermal emission is basically coming from the jet interacting with the medium, which we call the jet afterglow. The jet drives a shock in the medium, accelerate the electrons in a power law distribution, and those electrons cool down via synchrotron emission, and it produces this beautiful synchrotron afterglow. The kilonova is more like spherical and it's slower than the jet, but eventually concentrating on the non-thermal emission part, the kilonova ejecta will basically create the same synchrotron afterglow as the jet afterglow, but at later times, which we expect to see and which will later come in my presentation as well. Okay. So the story at like 900 till 900 days, we could see that all the observations, these are just different. This is the light curve, and these are all the frequencies, radio and optical and X-rays. And we can see that the structure jet model, which are these bands here, the observations fall on top of that, which is great because that model really explained really well the observations till 900 days. What's happening at 1200 days is something which is exciting. So in X-rays, you can see we still have a detection, which is great. And obviously it is so close to us that we can still detect X-rays. And then in radio, although we do not detect anything, it wasn't like here we cannot see anything. Okay, so what happens when we plot these observations at 1200 days on top of the structured jet model? I'll come back to the orange and the gray light curves soon. So the structured jet model, the blue curve is the best fitting structured jet model we have. And if I zoom into the latest observations, we can see that at 1200 days, so at 900 days, it is still like within 1 sigma-ish consistent with the model. But at 1200 days, we do see like a significant deviation from the expectations of the structured jet model. So we perform a couple of statistical tests in my paper, and we conclude, and we perform statistical tests both with a jet model approach and like using a jet model agnostic approach. So we have like robust conclusion, and the robust conclusion is that it has like at t greater than 900 days, we see a deviation from the structure jet model at 4-ish sigma Gaussian equivalent level. So obviously, because the radio was a non-detection, we do not really know what's happening there. Moving on to the spectrum, the SED, as you can see, this is a beautiful plot. And as you can see, it is throughout the 1,000 days, the SED has been just a straight line. And so we can constrain the slope of the straight line really, really well. We have a very good handle on it. And hence the value of P, which is just the distribution of the electron population. So the power law index, sorry, P is the power law index distribution of the population of electrons, which we constrain it as like 2.166. Okay, but what's happening right now at 1,200 days? So this is the SED at 3.4 years after merger. And if we extend this X-ray observation to the radio wavelengths, and this is the red line is the best fitting curve from my previous slide. And sorry, was it a question? Okay. So because the radio was a non-detection and therefore it's an upper limit, we can see that the SED is actually getting shallower now. So the value of P is reduced and the spectrum is getting harder. So it is spectral evolution. Finally, we can see some kind of change in the SED, but it's not the kind of spectral evolution we would have wanted to add constraints and solve the degeneracy within the parameters. But it is something, so that's really exciting. So combining these two observations, observing the X's in the X-rays and then the spectral hardening, what could basically explain, what coherent picture could explain these two observations together. So in my paper, we discussed 3 possible sources. The first one is the intuitive thing, the natural evolution, you know, maybe it is the late time evolution of the jet. Or it could be one of the 2 really interesting and exciting scenarios. It could be either the kilonova afterglow, which I talked about earlier, or it could be the central engine powered radiation. So maybe we are seeing, you know, something from the remnant itself. So both of these scenarios are quite exciting. So let's dive in. The first one, is it the late time evolution of the jet? The short answer is no, but we do discuss one by one what could cause, what could possibly cause it, but why it's not giving you, but why it's not the right answer. So the first one is overdensity. So maybe the jet encountered an overdensity, which could happen. Suppose if one of the companions of the neutron star, one of the companions of the system is a pulsar. So a bow shock cavity can be produced by the pulsar wind, and the jet has been traveling through it up until now, but it has suddenly encountered the edge of that bubble. And that could create like an overdensity scenario, but we would need a very, very steep density gradient. So we need an increase in the density by a factor of 10 to the 8 over parsec scale, which effectively means that a mass of greater than 10 solar masses should be contained within the jet angle, which is really unfeasible. So, you know, that is basically ruled out based on that argument alone. But also, if we do some mathematical thing and we calculate the radius of the shock cavity using the density of the external medium, we find that the shock of the cavity is the calculated shock of the cavity, sorry, the calculated radius of the shock cavity is actually less than where the jet is supposed to be right now. So it is kind of contradictory, so we rule that out. What about the energy injection scenario? So to create that excess and X-rays, we would need an energy equivalent to the jet kinetic energy at this point of time, which is, again, there is no proposed source which could explain that amount of energy injection at such late times. So we rule that out as well. Now, we can increase epsilon B and epsilon E, which are just shock microphysical parameters, which are basically the fraction of energy that goes into the electrons and the magnetic field. So we can increase those to create that X's and X-rays, but there is really no reason. So it would require an ad hoc evolution of these parameters, which is again unfeasible. Just a note that all these three scenarios also do not explain the spectral hardening of the basically spectral hardening. The fourth one is more plausible. It's like, it's transition to non-relativistic phase, and obviously the jet is slowing down. So eventually it's going to enter the non-relativistic phase, but that's going to happen much, much later. But we could see like signatures of the transitioning happening, and that could also explain the spectral hardening really well, because in theory, the non-relativistic shock would have like a P which is closer to 2. So obviously that would explain the spectral hardening, but to explain the X's in the X-rays, you would need epsilon E and epsilon B to either remain unchanged or increase, and there is no reason for them to not decrease. So again, like all of these cases are basically unfeasible, and they require ad hoc evolution of these system parameters. So we basically rule this whole thing out. The jet late time evolution of the jet is not the answer. Okay, before diving into the really exciting scenarios of the kilonova afterglow and the accretion, or like the central engine powered radiation process, this is like a very basic slide. Sebastiano has already alluded to the different outflows, the different ejecta in his presentation. So this is basically just a refresher that, there's a significant mass material ejected on dynamical scales and on secular scales, and all of these outflows will have different compositions, different masses, different velocities, and based on what electron fraction the ejecta has, it would produce the red kilonova or the blue kilonova, or actually have the R process going on in it. Two important things of that ejecta is, however, that there is a very small portion of the ejecta which can be driven through shocks at very, very high velocities. So it will like basically be ahead of everything else. And that has an important implication on the kilonova afterglow, which I'm going to discuss. We also call this the fast tail of the ejecta, because it's like the fastest tail of the ejecta. And this cannot be probed via thermal emission. The only way to probe this is through the non-thermal emission, through its interaction with the medium, just like the jet afterglow. And the second point is that up to 0.1 solar mass of material can actually be become gravitationally bound to the remnant and produce a disk. And it can have implications on the central engine powered radiation scenario, which I'll discuss later. Okay, so could it be the kilonova afterglow? If it is the kilonova afterglow right now, we do need the fastest tail of the ejecta to be really fast enough to produce the afterglow at this time. So let's keep that in mind. But we explore this scenario in two ways. We do it analytically by parameterizing the energy distribution within the ejecta to be a power law in momentum space with the index alpha. So in theory, a lot of people are trying to find out what actually the alpha values, they're the ones which could explain most of the this ejecta. But from here, in this, coming back to these light curves, you can see that we have orange lines which with different alphas, and these set of lines are for fixed extrinsic parameters, and extrinsic parameters are just the ambient density, the shock microphysical parameters, and the energy. And from the light curves, we can say, alpha 4 to 6 is kind of explaining the observations. But in reality, if we explore the whole parameter space, because we do not have constraints on the shock microphysical parameters or the ambient density, we can see that alpha, all values of alpha from 2 to 10 can basically explain the observations, which just means that we cannot really constrain one system based on these observations, and we need more of them. Second, the second thing we tried is actually it was done by Sebastiano's student, Zevalot, and we basically employed ab initio numerical relativity simulations of BNS mergers, and we created more realistic kilonova ejecta profiles with different equation of states and different mass ratios. So you can, like from this top plot, again, these have different equation of states and different mass ratios, but the extrinsic parameters are fixed. And from this plot, you'll say, okay, you know, maybe this yellow afterglow is, the yellow system is actually satisfying the observations. But if we allow the extrinsic parameters to change, but keep the mass ratio the same, and we see with different equation of states, actually all of them can explain, you know, these observations. So similar to the previous situation, we cannot really constrain it to one system that's explaining these observations, and we need more of them. Okay, but one of the important, really important conclusion of all of this, a system where the remnant collapses to a black hole promptly are disfavored. So simulations show that systems where this happens, they create either really, really bright kilonova afterglow at this point of time, or the peak is at really the peak of the kilonova afterglow is at like really, really later times. So they do not satisfy what's happening right now, which is great. At least we have one constraint here. Okay, two other really important implications of if it is the kilonova afterglow, and like two open questions about it was, is there a neutron precursor emission? So what happens is if, and these are like the ejecta profiles, and you can see the distribution of energy with the momentum and the mass, with the velocity. And you can see that there is some portion of the ejecta which has velocity greater than 0.6 c. And in the free neutron case, basically it has a velocity 0.5 c, greater than 0.5 c, and it's massive enough. So these are the requirements. This blue shaded area, it falls in the requirement where the ejecta, where a small part of the ejecta is massive enough and is fast enough that it will escape the remaining bulk of the ejecta, and neutrons in it will avoid capture. So neutrons in it won't be captured, and therefore the neutrons will be free, and they'll beta decay, and they'll create this very bright UV transient, but on an hour time scale. So because we did not observe anything in optical or UV in the case of GW17 at 17 for like up until 11 hours, we do not really know if that exists. And the second very important implication is it could help us answer where the gamma rays were coming from. So Or Gottlieb in his 2018 paper proposed the scenario where the gamma rays were coming from the cocoon shock breakout. The cocoon was inflated by the jet when it was going through the ejecta. And so we should have like a fast enough tail of the ejecta for that breakout to happen at the time. And basically it would explain the delay in the gamma rays and the gravitational wave trigger as well. So if it is the kilonova afterglow, you know, it will have really great implications on both of these scenarios. Okay, moving on to the last one. What if it is the central engine powered radiation? And so if it is not the kilonova afterglow, it could be that we are looking at the accretion process that's happening. So one of the scenarios is, you know, the remnant is a black hole now, and there is an accretion disk around it. And if the fallback happens, a fallback is happening gradually, then we can see that radiation coming through, because at these times we also expect the kilonova ejecta to be transparent to X-rays. And the observed luminosity of the X-rays right now at 1234 days is 5 times 10 to the 38. And the Eddington luminosity for a 2.5 solar mass black hole, which is the derived remnant mass for GW17 is 8 times 10 to the 38 ergs per second. So it's really close, but it's lower than the Eddington luminosity. So it's consistent with you know, the radiatively efficient accretion process happening. And also the effective temperature of the thermal disk emission is at 2 keV. So it's right within our Chandra X-ray band where we observe this luminosity. So all of these things combined, it could explain what's happening. It could explain our X's and the X-rays at these timescales, but also to avoid violating the kilonova emission, the kilonova thermal emission at earlier times, when the kilonova ejecta might not have been optically thin, the X-rays would have reprocessed to the UV and optical. So it could violate, but we need the accretion processes happening at earlier times to be less radiatively efficient, to not violate the luminosities in the kilonova. So this is a very plausible case, and if this is the case, it would be the first time we would ever see this phase of evolution in the BNS merger. So that's really great. The energetics argument, we do discuss the spinning magnetar scenario, although the energetics agreement, like the energy is 10 to the 51 erg, and the energy of the kilonova is 10 to the 51 erg, and then there was a jet launched. So all of these point to a remnant that basically collapsed to a black hole within a second or so, and disfavor a long-lived magnetar. But for completeness, we do go through this, and we see that the spin down timescale, the natural spin down timescale, or with the fiducial parameters, is 150 seconds. To basically make the spin down timescale to 1,000 days, which is basically right now, which could create the X's, we need a magnetic field which is really, really low. And it is in contradiction to the expectations of the magnetic field amplification, which happens in the BNS merger simulations. So this is not really a favorable scenario that happens. But accreting black hole is a really, really plausible thing. So future observations, and we have planned future observations in this December. So they will obviously, they will help us to provide, give us more conclusive evidence of what's happening. In the case of kilonova afterglow, we would see the X-ray and the radio emission brightening with time, whereas in the accretion case, we would see that the X-ray emission would remain either constant or it will decay with time. So, and we would not see radio. So if you compare, there was one point. So if you compare the, this situation of accretion with the ultraluminous X-ray sources or the X-ray binary, which are accreting in soft state, there the radio is significantly quenched. So if you compare this situation with those situations, we can explain, why the radio is quenched and why we probably might not see radio in the future. And in the kilonova afterglow scenario, because kilonova, the fastest tail of the ejecta is still slower than the jet, it would have the P, which will be lower, so it will naturally explain the spectral hardening. So obviously these things have, both these situations have their pros and cons, but future observations will clearly distinct between them, and we'll see what's happening. So yeah, thank you.
Thanks a lot, Brigitte, for this very interesting talk and these exciting results. There is a very short time for a very quick question. So if not, maybe some question will arrive later, please chat in the chat box, and so Brigitte can answer to you. And then we move to the last talk of this section, that is Jonathan Quirola Vasquez, and he will talk about extragalactic fast X-ray transient candidates discovered by Chandra.
Hello, can you hear me?
Yes.
Okay. Hello everyone, my name is Jonathan. I am a PhD student at Pontificia Universidad Católica de Chile. My advisor is Franz Bauer, and currently I am also working with Professor Junker's group at the Radboud University. So today I will talk about fast X-ray transients, some of them related with binary neutron stars. So that is the reason of this title. So like an introduction, so X-ray transients are related with a different kind of astronomical objects in different energy, time, distance scales, essentially, from stars, neutron stars, AGN. And they are very important now to try to understand well the nature or a wide type of astronomical objects. So particularly, I am focused in fast X-ray transients. These events that you can see in this plot cover a large range of times from minutes to hours, and also a range of X-ray energies. And we have different kind of events that could be related with these fast X-ray transients, like shock breakouts related with core collapse supernovae, tidal distribution events, gamma ray burst, for instance. So in this talk, I will try to focus on fast X-ray transients and particularly binary neutron stars. And like motivation of our work, it's related with these 4 fast X-ray transients. I will explain very quickly, more or less, some of them. All of these events were identified years after the trigger, so was not possible to follow up these events and try to look more or less the real nature of them. So we have several scenarios that could be explained their properties that I will explain now. So the first of these transients, it's called XRT 000519, was discovered by Jonker and Doll in 2013. In here you can see the likelihood of this event, so and also the position in the sky of this event. This event occurred very close to the M86 galaxy. So was related with this galaxy. This galaxy is at a distance of 16, 17 megaparsecs. And in here you have the likelihood. You have a main peak, the luminosity peak, assuming this distance to M86, it's 6 times to the 42 Earth per second. And if you look before the main peak, you have two important, two flares before the main peak that could be related with previous events related with the main emission. And in here you have a close-up of this main peak, and it is clear a double peak substructure that could be in the main peak. So if you compare this luminosity peak of this event to the and we consider that it's equal to the Eddington luminosity, we can constrain a mass of 10 to the 4th solar masses. So this event, the best explanation for this transient, it's maybe related with a tidal distribution event involving an intermassive black hole and a white dwarf. However, some of the properties of the event and also the host association that we are considered with M86 tell us that maybe this tidal distribution scenario is not the only one. So we have several uncertainties related with these fast X-ray transients. So some authors also try to even explain this event like a gamma ray burst. However, maybe at this point, the best scenario is tidal distribution events. The same case of this other transient, XRT 110103, identified by Glenn in 2015. The nearest galaxy for this event is this object that you can see here, ACO 3581, and a distance of 96 megaparsecs. And if you look also the light year of these events, also we can find a very strong main peak, also with a peak flux very similar to the previous one. However, the main peak does not show a double peak structure like the other fast X-ray transit. The luminosity peak related with this event reached a luminosity of 10 to the 44th Earth per second, so 2 orders of magnitude higher to the previous one. The properties related with this transient may be also associated with a tidal distribution, but with a different black hole mass or maybe a different beaming factor. However, also this uncertainty related with the galaxy host also permit us to probably consider additional pictures to try to explain this event. These both events are open questions that we have now, and we try to study more in detail. The ratio of these two events that show very similar spectral and timing properties, it's 10 to the 5 events per year to the whole sky. That was computed, considered all the data that was possible to identify at the time of these transits from Chandra. And now I will explain two additional transients. The first one is XT1, published by Bauer et al. In 2017. This is a very interesting transient because it was discovered in the Chandra deep field south. And here you have the likelihood of this event. It is clear that after 100 seconds, the number of counts and also flux or luminosity increase very fast, and after that they start to decrease. The T90 time, the duration of this event is around 5 kiloseconds, and was possible to identify the host galaxy of this event clearly. And here you have the X-ray image of the transient, and here you have you can see a HST image. It is clear that inside this 3 sigma error detection, you have a faint object that is really it's the apparent host of this transient. Was possible to obtain the photometric ratio of this event. So this transient could be occur between a ratio of 0.4 and 3.1. And after that, they try to classify this event. And here you have the likelihood of the event in flux units and in luminosity units, and a comparison with other kind of transient like GRBs. In this case, this to the background histogram. Shock breakouts, in this case, this green solid line, and a couple of tilde distribution events. And if you look in luminosity units, it is clear that maybe this event it's it's an under luminous transient if you compare with gamma reverse. Also, it is possible to more or less discard this association, the association with short breakout, because the difference in luminosities. So after analyzing the different optical, X-ray data, was possible to conclude that maybe the best scenario is that this transient could be related with that off-axis short gamma reverse. However, other scenario related with data distribution events of intermassive black holes and white dwarfs, it's not discarded also. And again, other fast X-ray transient, very interesting, called XT2, also was identified in the Chandra deep field south. This event has a T90 of 11 kiloseconds, and in here you can see the likelihood of this event. This event showed a very different likelihood if you compare with ST1, the previous one. It showed a plateau with a duration of 1 or 2 kiloseconds, and after that a decay with time to the -2, how you can see here. Additionally, if you look how the hardness radio of this event evolves with the exposure, it is clear a softening trend in the hardness radio, how you can see here in the bottom panel. Additionally, this event was possible to associate with a host galaxy, and was possible to identify the spectroscopy redshift at 0.74, and with that, the offset related with this event, an offset of 3.3 kiloparsecs. So consider this, sorry, a question? No? Okay, so consider this timing and spectral properties, and also the properties of the host galaxy, for instance, the offset. And here you can see how the offset of this transient respect to the host galaxy falls very well with the histogram of the short gamma reverse that show that was possible to measure an offset. Was possible to associate this, consider these properties with short gamma reverse, and also the interpretation of this data of this transient also comes from the shape of the light curve. If you remember, the light curve show a plateau during some 1 or 2 kiloseconds, and after that a decay. This is the typical plateau that it's we know from the afterglow of short gamma reverse, and typically is related with the emission of a millisecond magnetar. Yeah, the typical equation for explain this luminosity is this one. So maybe it is probably, some authors argue that exists a relationship between XT1 and XT2. You remember, XT2 showed this plateau and the decay. However, it's not the case of XT1. So maybe, according with Sun et al. In 2018, the connection between them is that both fast X-ray transients comes from the X-ray emission of a magnetar, a massive magnetar formed after the merger of two neutron stars. And the difference between the light curve, the plateau in the XT2 and this fast increase in XT1, it's because it's depend of the line of seen respect to the on axis. So in the case that we are looking XT1, probably the observer it's in a direction where the X-ray emission have to pass from an ejecta material. This ejecta material eventually could be absorbed part of the emission, the X-ray emission of the magnetar, and after some seconds, this ejecta is expanding and eventually becomes optically thin, and the X-ray emission could be travel without an absorption. So this ejecta material that absorb and obscure the X-ray emission could be explain this fast rise in the light curve. And in the case of XT2, the observer is in very close to the jet axis, so we are looking directly in the magnetar emission that could be explained the plateau. However, this interpretation is not the only one. Some other authors argue related with a different kind of data distribution events, for instance. So what is considered this for previous transients, or ideas to try to find similar objects in the Chandra and XMM Newton catalog. So previously, some authors tried to find a fast X-ray transient in the XMM and in some Chandra catalogs. For instance, Albert Larsson searched events in the XMM Newton data, and they found 12 fast X-ray transients, and all of them apparently identify like shock breakouts. However, it is important to try to verify this for some uncertainties in the X-ray detections. And also Yang et al. In 2018, they tried to find similar transients in some Chandra surveys that you can see here. But unfortunately, they don't find fast X-ray transients like the previous ones. So we try to find this kind of transients. So for that, we consider the Chandra data release 2.0 that in the Chandra data release, you can find information from the Chandra before December 2014. So we analyze all the sources, 200,000 events, all of them outside the galactic plane. And the method that we use is practically try to find cone excess in the different light curve of the transients. So practically we split the different light curve of the events in different regions, and we try to find an excess in the different time windows that we consider. So to try to prove our method, we apply to the previous extragalactic transient that we know, and we recover them. So additionally, to try to clean our sample from young stellar objects that also mimic the light curve of these extragalactic transients, we consider additional X-ray observation from XMM, XLT Swift, and also we use catalogs in other energies to try to discard stellar stars, essentially, young stars. So after applied all these filters that we consider, this is the position of the fast X-ray transients that we obtain analyzing all the data of the Chandra source catalog 2.0. We found 14 fast X-ray transients identified outside, consider only the events outside the galactic plane that you can see here. And like some of the results that we obtained. So you can see here from this 14 events that we found, 5 of them was related um, um, with local galaxies, essentially galaxies near or with a distance less than 19 megaparsecs. So it was possible to constrain very well the X-ray, the luminosity peak between 10 to the 39 and 10 to the 40 hertz per second. So we can discard the association of these 5 fast X-ray transients related with local events with show breakouts or GRBs or data diffusion events by the luminosity range that we obtain. However, the other events that we classify like distance because they are not related with local galaxies, and also we discard the possibility that they come from stellar flares from stars, essentially. However, we have a couple of problems with that. Only 3 of them was possible to identify extended association. So in other words, host galaxy, and it was only in these 3 phases transients was possible to measure a spectroscopy or a photometric redshift that in these 3 cases was between 0.7, which means that this transient has luminosity peak of 10 to the 44, 10 to the 45 hertz per second, more or less. So with this information, the rate of these events, it's in the order of 10 to the 6 events per year in the whole sky. So in here you can see how the density rate of these events evolve with redshift. In the case of the events that are related with local galaxy, was possible to compute the local event rate that you can see in here. This is and also in the case of the events that we only have, in the case of the 3 events that we have only the redshifts, was possible to measure the density rate at the maximum distance that in this case Chandra can look. If you compare this value with the previous values obtained from the rates of XT2 or XT1, this value match well with what we can expect. However, some of these events that was not possible to measure a redshift at this point maybe are related with XT2 in the sense that their timing and spectral properties share similarities with XT2. These 3 events show a plateau and also a decay very similar to XT2, and also this behavior of the harness. You have a softening in the harness similar to XT2. So these properties, these timing and spectral properties, suggest a relation with XT2. And if you remember, maybe XT2 could be related with the magnetary emission related with a short gamma ray burst. However, because we have these uncertainties at this point of the redshift, it's not possible to rule out or know this scenario. In this plot, for instance, you can see the Lie curve assuming different redshift, 0.5 and 2, the mean values for short and long gamma ray bursts, to look more or less what if these events are related with binary neutron star or GRBs, essentially. The location in the comparison with other kind of transients, for instance, short GRBs, the purple lines, or the gray lines, long GRBs. So these events also share this low luminous light curve similar to XT2. However, we have to confirm this with the new redshift that we will obtain soon, I hope. Additionally, now I will talk about 2 more transients that these transients are outside the Chandra data release 2.0. They was discovered in 2017 and the other one in 2021. So we don't analyze with the original data. However, we identified also using our methods. This transient is called XRT 70831. And in here you have the light curve of this event, and this event is very similar to XT2, how you can see here. A plateau with a duration of 1 or 2 kiloseconds, and then a decay, essentially. This event also was possible to identify the host galaxy using HST data, how you can see in here. In here you have the 3 sigma Chandra error position, the red circle, and also this is an extended object that must be the host galaxy of this event. This event was possible to identify obtain a spectra of this extended object. However, we have only isolated emission line, so we have two possibilities for the redshift: a redshift of 0.64 or 1.89. At this point, we need additional observation to try to discard one of these two possibilities. And taking into account these two redshifts, the projected distance, the physical offset between the position of the transient and the host galaxy, it's in order of 3.6 or 4.5 kiloparsecs. And if you compare with the expected offset of long, short GRBs, this offset match well with short gamma bursts. So if you consider, again, the timing properties, the spectral properties that are very similar to XT2, which was related with binary neutron star, maybe XRT78 0831 could be also related with short gamma bursts, maybe. So in here you have the likelihood of this event, assuming these two redshifts, 0.64 and 1.89, and a comparison with long GRBs, short GRBs, and also XT1, the blue one in here, and XT2, the orange in the background. So this event also share similar properties that some of that XT2 and some of the short gamma bursts. Taking into account these two redshifts, the peak luminosity of this event could be 10 to the 45 or 10 to the 47, which falls very well in the range that we expect for GRBs essentially, and also similar to XT2. And finally, I will talk about this fast X-ray transients 21, 04, 23. This event was detected recently on December 2000, in April 2003 of this year, and was a serendipitous detection by Chandra. And if you look in here, the likelihood of this event, again, you can see a plateau and also a decay, very similar to XT2, and again, the similar harness radio evolution, a softening trend in them, how you can see in here. We try to follow up this event 2 weeks after the trigger. And here you can see the observation that we obtained with FORCE2 and GTC in R and J band respectively. And here the position of the transient, and it is clear that we cannot find a counterpart for the transient. We only have upper limits essentially. However, these two sources that you can see here in FORCE2 image and also in the GTC image, this could be the possible, these are extended objects that eventually could be the host of this event. To this one, we measure the spectroscopic redshift of 1.5. That could be the host of this event. And taking into account the redshift, this redshift of 1.5 for this event, we can obtain a luminosity peak of 6 10 to the 45 ergs per second, very similar to XT2 again. And here you can see that again we have these similarities with the likelihood of some short gamma bursts. However, we need additional observations to try to measure better the offset between the location of the transient and the host and the possible host galaxy to try to discard enough other possible pictures to describe well this fast X-ray transient. Okay, finally, like a conclusion, we try to identify these 14. We identify these 14 fast X-ray transients hidden in the Chandra source catalog 2.0. Maybe we have a mix of origin related with these fast X-ray transients. However, some of them show properties that suggest that could be related with short gamma bursts. This is very important because we hope that with the next generation of X-ray emissions, we can detect fast X-ray transients, for instance, using the Einstein proof satellite that will fly the next year. And with that, we can detect phase retransients, where one of the subpopulation of phase retransients could be related with binary neutron stars. So it is important to try to characterize them. Additionally, it is important to try to use, try to observe some of these hostless events that we have now to try to find the host galaxy, identify redshift, and with a distance. And in that case, we can't rule out the scenario that we are proposing here. And additionally, we have events that are outside the Chandra source catalog. However, also they show similarities with AXD2. So also this could be related with binary neutron stars. And finally, the idea is to try to apply our methods and try to find an additional observation beyond the Chandra, the Chandra source catalog, and also apply to XMM Newton or XRT observation to try to mining data. That's all, and thank you.
Thanks a lot, Jonathan. We have basically no more time for a question because I have received a message. They will close the Zoom room, but thank you very much. This was really very exciting. And in fact, I have a question. I will try to make it, but if not, maybe we can write. Wondering if it is a magnetar, you can assume with some fiducial parameter the luminosity in X-rays and try to find the distances of this known source. I'm wondering if you have done this by assuming magnetar.
Yeah, and of course, all the time in our group discuss that probably magnetar models also can explain all the data. However, yeah, that is one thing that essentially we have to do, and we are working on that.
Okay, thanks a lot. So we are still here. So maybe someone want to try to make some question before they close the Zoom room. Okay, so if there are no questions, I thank you very much all the speakers for this very, very interesting parallel session and to have accepted our invitation, and hope to meet you in person soon in the future. So thanks a lot, everybody, and see you soon.
Thank you.
Bye.
Thank you. Bye.
Thank you.
Thank you.
Bye. Thank you.